Throughout your career as a pilot, you will most likely fly a variety of airplanes, ranging from small single-engine trainers up to the very large multi-engine jet transport airplanes. It may seem obvious, but these airplanes not only look different from one another, but more importantly, they vary significantly in their performance. The reason for this is that different aircraft are designed to fulfill different roles. The nature of these roles plays a big part in the level of regulation and safety imposed by the aviation authorities on these airplanes. For example, if an airplane were designed to carry a large number of passengers over a long distance at high speed, the consequence of its performance failing to meet the prescribed standards would be catastrophic. It's therefore prudent to ensure that the very strictest performance rules are applied to these types of airplanes. To achieve this aim, the aviation authorities have segregated airplanes into certain classes, so that the authorities are better able to apply the associated level of performance regulations and ensure a greater level of safety. To this end, 4 principal classes have been established for all public transport airplanes. These are Class A, Class B, Class C, and lastly, unclassified. We'll examine Class A airplanes first. Class A is used for all multi-engine turbopropeller airplanes having 10 or more passenger seats or a maximum takeoff mass of 5,701 kilograms or more, and includes all multi-engined turbojet airplanes. This class of aircraft meets the European Aviation Safety Agency certification specifications for large airplanes, as detailed in CS25 Book 1. The performance regulations for Class A airplanes are the most stringent of all the classes, and must take into account reasonably expected adverse operating conditions, such as takeoff and landing on contaminated runways. Engine failure in all flight phases must also be a prime consideration. Should an engine failure occur, the airplane must be able to land at a suitable airfield so that a forced landing is not necessary. The reason for these strict performance regulations is simply due to the fact that this type of airplane carries the greatest potential for performance failure risk because of its high speed and high potential passenger loads. Airplanes which fall into this class range from the small business jets to the huge Airbus A380 and the Boeing 747. The airplane we will be examining in detail when analyzing this class is the Boeing 737-400 and 737-800 series, as shown here. The second class of airplane for public transport is Class B. This includes all propeller-driven airplanes having 9 or fewer passenger seats and a maximum takeoff mass of 5,700 kilograms or less. This class does not meet the European Aviation Safety Agency certification specifications for large airplanes, and can include both single and twin-engined airplanes. The performance regulations for this class are not as stringent as for the Class A airplane, but they still include allowance for engine failure in all flight phases as for the multi-engined airplane, except below 300 feet. This means that should an engine failure occur above 300 feet, the aeroplane should be able to land at a suitable airfield without a forced landing being necessary. However, because a forced landing will inevitably result from engine failure on a single-engine airplane, they are not permitted to fly at night or in IMC or in such areas where a suitable landing surface is not available. Examples of this class of aircraft are the PA-28 Piper Warrior, the Beechcraft Bonanza, and the twin-engined Piper Seneca. The single-engined airplane we will be using when analyzing this class is the Beechcraft Bonanza. The multi-engined aircraft will be the Piper Seneca II, as shown here. The third class of airplane is Class C. This class includes all piston-engined aeroplanes with 10 or more seats or a maximum takeoff mass of 5,701 kilograms or more. This class has similar regulations to the class taking into account reasonably expected adverse operating conditions, such as takeoff and landing on contaminated runways, and consideration of engine failure in all flight phases. Examples of such aeroplanes include DC-3s and DC-6s. However, for the JAA Airline Transport Pilot License Performance Exam, no more detail is needed for this class, and it forms no part of the learning syllabus, since there are very few aeroplanes of this type operating in the public transport category. The last class of aeroplane is the unclassified class. This caters for those aeroplanes whose design affects their performance in such a way that they cannot comply with the previously mentioned class regulations. Such aircraft include seaplanes and supersonic aircraft. The class unclassified does not mean that these aircraft do not have performance regulations. They most certainly do. It's just that these regulations have to be tailor-made for each individual type of aeroplane concerned. As with the Class C, this class is not examined in the JAA ATPL performance exam and is not part of the learning syllabus.
In this lesson, you will learn what is meant by performance standards, how performance standards are derived, and the purpose they serve. Performance standards are laid down by aviation authorities in two principal ways. The first is a level of regulation which ensures that the aircraft is airworthy, in other words, safe to fly. These are the certification specifications and are set out in the document from EASA called CS25. The second level of regulation is to ensure that the aeroplanes are safe enough to operate in the public transport role. That is, they are safe enough to carry fare-paying passengers. These are the operational regulations. Both of these performance standards together aim to achieve an appropriate level of safety.
What is an appropriate level of safety? This is a difficult question to answer since some performance-related incidents involving passenger-carrying aeroplanes are actually very minor and do not dramatically affect the aeroplane or its passengers.
Whereas other performance-related accidents are catastrophic, causing massive structural damage to the aeroplane and loss of life. It is therefore essential to enforce safety regulations of a stringency which will ensure that the possibility of a passenger-carrying aeroplane suffering a catastrophic performance-related incident is so small that it will hardly ever occur. To this end, the authorities have laid down guidelines appropriate to the consequences of various possible performance failures. Looking at the information on screen, we can see that if there was a performance failure which resulted in a hull break with multiple fatalities, this would be classified as catastrophic. The possibility of catastrophic performance failure must be so small that it should only occur once in more than 1 billion flight hours. Aeroplane manufacturers must abide by performance regulations laid down by the authority in order for the aircraft to be given its certificate of airworthiness. For example, large aeroplanes, principally Class A aeroplanes, must abide by the certification specifications laid out in EASA in the document CS25, and Class B must abide by the certification specifications in CS23. To achieve this, rigorous testing of the aircraft must take place by the manufacturers. It is a very lengthy and costly process, but one which is absolutely vital for safety. These pictures show various aircraft being tested under various conditions. The scope and depth of regulations are extremely detailed, but the certification specifications for Class B are not as stringent as for the Class A. In order to gain an airworthiness certificate, a brand new Boeing 737 would have undergone a far more rigorous set of tests than a Cessna 172, and yet both could potentially be used for public transport. Therefore, a disparity in the level of safety exists between the types and classes of aeroplanes, even though they may be used for the same purpose. This situation has been addressed by the aviation authorities, laying down another set of performance regulations, applicable only to aeroplanes that will be operated for public transport and detailed in JAR Ops. These are the operational regulations. JAR Ops Part 1 prescribes requirements applicable to the operation of any civil aeroplane for the purposes of commercial air transport. Since Class B aeroplanes are not subject to very stringent certification specifications, they therefore have the very strictest operational regulations applied to them. This was briefly mentioned in the previous lesson when we stated that single-engine aeroplanes are not allowed to operate as public transport at night or in IMC. Class A aeroplanes, on the other hand, are subject to very stringent certification specifications and will, therefore, have the least stringent operational regulations applied to them. They are allowed to operate even in the poorest conditions. To summarize, CS25 and CS23 are the certification specifications for Class A and Class B aeroplanes respectively. However, if these aeroplanes are to be operated for public transport, then they must also abide by JAR Ops Part 1 as well, which constitutes the operational regulations. The certification and operational requirements together aim to ensure that there is only one chance in over 1 million that an aeroplane will not be able to meet the minimum performance standard required for a given mode of operation.
Throughout this course, and in all performance regulations, you will come across a variety of different expressions of performance that need to be understood and explained.
Going through these will also help to clarify some of the ideas we have already covered. The first of these expressions is measured performance. Earlier on in the lesson, we mentioned the rigorous testing that aeroplanes go through before they are issued with an airworthiness certificate. A large part of these tests involve discovering the aeroplane's performance capabilities. These include finding out its average takeoff distance, landing distance, climb gradient, range, and so on, under a variety of different weights and environmental conditions, with a brand new aeroplane flown by a highly skilled test pilot. These particular performance figures gained by the manufacturer under strict test conditions are described as measured performance. However, measured performance values are an unrealistic representation of what may be achieved under airline operating conditions. This fact makes measured performance values somewhat meaningless to the airlines. Airlines do not always have brand new aeroplanes, and their flight crews are not all test pilots. Therefore, it seems obvious that another set of performance values are needed to more accurately account for this variation. To more accurately reflect reality, the measured performance values need to be reduced by a factor which reflects the condition of a representative operating fleet of aeroplanes flown by line pilots.
When this factor is applied, we get what is known as gross or demonstrated performance. Gross or demonstrated performance is defined as the average performance that a fleet of satisfactorily maintained aeroplanes flown by an average pilot can be expected to achieve.
To help understand the difference between measured and gross performance, we will use an illustration involving an aeroplane landing. Shown on screen is a representation of a landing using the measured performance values, which, if you recall, is flown by a test pilot in a new aeroplane. However, we mentioned earlier that this was unrealistic. So if we now carry out a landing using gross performance figures based on an average pilot with an average aeroplane, you can see that the landing is not as good. This time, the landing has used up more runway. The average pilot, in his average aeroplane, has not performed as well as the test pilot with his new aeroplane. This image, comparing measured and gross performance, gives you a much clearer idea of what the different performance values mean. You will probably appreciate that it would be far more prudent to use the gross performance data rather than the measured performance data, since gross performance is the performance that most pilots would achieve. However, even though gross performance values are more fully representative of operating conditions, there is still one more issue concerning gross performance which is a concern. We now appreciate that a talented, well-rested pilot with a new aeroplane will perform a better landing than that represented by the gross performance shown on screen. But from what we have learnt so far, we may also deduce that a less able pilot, who is perhaps tired and flying an old aeroplane, will perform even worse than the gross performance. This is a potentially hazardous situation, and as demonstrated in our example on screen, would result in the pilot almost running out of runway, endangering the aeroplane and its passengers. If the published landing data in the aeroplane flight manual was the gross performance, the pilot in this case would not have achieved it, and thus will have compromised safety. He was expecting to perform as in accordance with the manual. So even though gross performance is a more useful and realistic indicator than measured performance, we must ask ourselves, is even gross performance good enough to use in a typical airline environment? The answer, as you will probably have surmised, is that gross performance is not good enough. It just does not provide enough safety standards for public transport operations. What safety standards should the authorities enforce? Should the authorities take account of a bad landing every now and then and set a level of safety that allows for that, and include these values in the aeroplane flight manual? Is that good enough? Or should they take into account the worst landing in every 1,000? Or even every 100,000? Would that be good enough? Well, we mentioned earlier on in the lesson that the authorities aim to set a level of safety to take into account the worst case in every million. This level of safety is, in fact, the level taken as the safety standard for normal airline operations. The performance standard which represents this level of safety is called net performance. Because of the safety margin contained within the net performance figures, it is the net performance rather than the gross performance which is written into the airplane flight manual for use in airline operations. This means that the published data within the flight manual ensures that for over 99.99994% of the time, the performance achieved will be better than published. In order to determine this performance standard, the authorities will not, of course, carry out 1,000,000 landings or takeoffs. Rather, they will have statistical data stretching back for many years and from many aeroplanes. In the case of landing, this data will be plotted on a histogram, with landing distance on the bottom axis and frequency of landings on the left axis, as shown. There will of course always be a few good pilots who carry out very short landings, just as there will be a few who carry out very long landings. But most landings will of course be of a similar distance to that shown by the top of the bell shape on the curve. This is the average performance, which can be effectively considered as the gross performance. Through statistical analysis, the authorities are then able to extrapolate what will be the worst landing in 1,000,000 landings. This then becomes the level for the net performance. There will be a particular value that separates the net and gross landing distances. This value is known as the safety margin or safety factor. Knowing this safety factor enables us to make the necessary adjustments to gross performance data so we may calculate the net performance data. We will discuss this in more detail later. If we now return to our landing illustration, we can see a little more clearly how to quantify the net performance. Shown here is the gross landing distance. To find the net landing distance, we multiply the gross distance by the safety factor. You will be required to do this on a number of occasions throughout this course and in your aircraft performance exam. It is therefore important to understand where the safety factor has originated from. Most Class A aeroplane flight manual data has net performance. But for many Class B aeroplanes, the flight manual data is gross performance, and it will be up to you to calculate the net performance so that you can determine the actual level of safety. Be careful though. Net performance has several other names that you may come across which mean the same thing. These are scheduled performance, planned performance, or dispatch performance. In the last part of this lesson, we will confine ourselves to recognizing the difference between the gross and net performance in different phases of flight. You will recall that we calculated net performance by adjusting the gross performance by a given safety factor, always remembering that net performance is always inferior to gross performance. Shown on screen is a takeoff using gross performance data, i.e., the gross takeoff distance. Remember that net performance will always be inferior. A takeoff of inferior performance would mean you use more runway. Therefore, the net takeoff distance is longer than the gross takeoff distance, as shown. Let us now examine gross and net performance in a climb. Shown on screen is an aeroplane's gross climb gradient. From what you have learned, do you think net performance gradient will be at position 1 or position 2? Remember, net performance is always inferior to gross performance. Click on the number you think is the correct one. The net climb gradient would be position 2. Let us look at one more example. If the landing we see here represents the net landing distance, then will landing 1 or landing 2 be the gross landing distance? The gross landing distance is landing number 1. Hopefully, you will now be able to manually adjust the gross performance values using a given safety factor to obtain the net performance values, or vice versa. As a general rule, you will have to do this any time you use Class B performance data. This will be covered and practiced when we encounter such situations, but you may need to come back to this lesson to refresh your knowledge of the core differences between the different performance standards. In this lesson, we will focus on the aerodrome characteristics which govern the performance of the aeroplane. Characteristics such as runway length, width, and slope play an important part in determining not only the type of aeroplane that can operate from the aerodrome, but also what the actual minimum performance of these aeroplanes should be. First of all, a runway is not just a simple length of pavement. There are various distances associated with runways that need to be carefully explained and understood. The first of these distances that we must consider is the takeoff run available, otherwise known as TORA. The takeoff run available is defined as the declared length of runway, starting at the point from which an aeroplane can commence the takeoff, and ending at the nearest point which is unsuitable to bear the load of the aeroplane under normal conditions. In most cases, the takeoff run available is essentially the paved length of runway from one threshold to another. However, there are instances when the takeoff run available is not the length of paved runway, or in fact the distance from one threshold to another. For instance, large aeroplanes will use a portion of the runway to turn and line up ready for takeoff. As such, the start point of the takeoff will be some distance in from the edge of the pavement. Due account of this must be made by the pilot. In such cases, the actual takeoff run available will, of course, be less than the paved runway length and the distance between the thresholds. This type of takeoff run available reduction is published in the aeroplane flight manual and not in the aerodrome information documents. Reduced TORAs can also result from the close proximity of the runway edge to obstacles or roads. It would be unsafe for an aeroplane to apply full power when it is so close to such features because of the dangerous effects that jet blast may produce. As a result of these considerations, the threshold is not at the edge of the paved surface, but a little further in as shown here. However, the two most common reasons for TORA to be less than the length of paved surface is either because there is a variation in the runway surface strength, or because there is work in progress. When the threshold is not at its usual position on the edge of the paved runway, it is described as a displaced threshold. Information about the TORA would be published in the aerodrome charts, like the one shown here, but temporary changes in takeoff run available length because of maintenance or work in progress would be published in the NOTAMs. Always consult the NOTAMs so that you are kept up to date about the latest changes to the aerodrome conditions or to the airspace in which you operate. It may seem a very obvious statement to make, but you must ensure that your takeoffs are accomplished within the distance legally available to you, in other words, within the takeoff run available. Unfortunately, there have been many cases where, due to unforeseen circumstances involving engine or system failure, an aeroplane has gone beyond the limits of the paved surface and with catastrophic results. At most aerodromes, it is just the TORA that will be available to use for takeoff. But at large commercial aerodromes, there are other runway designators other than TORA which you need to understand.
For commercial and operational reasons, there may be an extension to the runway called a stopway.
A stopway is the defined rectangular area beyond the end of the TORA in the direction of takeoff, no less wide than the runway and centered upon the extended centerline of the runway, able to support the aeroplane during an aborted takeoff without causing structural damage to the aeroplane, and designated by the airport authorities for use in decelerating the aeroplane during an aborted takeoff. A stopway is regarded as being provided for infrequent use, and it consequently need not have the same load-bearing or wear-resistant qualities as the runway with which it is associated. In some cases, the natural surfaces will be adequate, while in others some land drainage, perhaps ground grading, or even light paving may be required. At some aerodromes, a stopway comprising of natural surfaces may be usable only on a seasonal basis. It is essential that you check the aerodrome information for such details. A stopway may be an economical substitute for what would otherwise have to be provided as paved runway to meet takeoff field length requirements of some aeroplanes. When comparable field lengths are required in each direction, it will be necessary to have a stopway at each end. Stopways cannot be used for any other purpose than bringing an aeroplane to a stop after an aborted takeoff. When lining up, a pilot must taxi to the threshold and start his takeoff run from there. Even if a pilot is taking off from the other direction, he cannot use the stopway as an extra length at the end of the takeoff run. Even when landing, the pilot must not use the stopway, either to land onto or use to come to a stop. To help the pilot recognize the stopway, it should be distinctly marked, as shown here. As a rule, the takeoff or landing run should always be started or stopped at the threshold. There is one exception to this rule. If a pilot sees the runway markings shown here before the threshold, then he may use this marked portion of the runway for the initial takeoff run, but it must not be used for any other purpose. There is one other additional type of extension that can be made to a runway. This is called a clearway. A clearway is defined as a rectangular area beyond the end of the Torah, not less than 152 meters wide, centrally located about the extended center line of the runway and under the control of the airport authorities. The clearway is actually the area underneath the clearway plane, which extends from the end of the runway with an upward slope not exceeding 1.25%, above which no obstacle or terrain protrudes. However, threshold lights may protrude above the plane if their height above the end of the runway is 0.66 meters or less, and if they are located to each side of the runway. The length of clearway will be the lesser of the following two distances: the distance to the first upstanding non-frangible obstacle, or frangible objects of 0.9 meters or more, or a distance equivalent to 50% of the Torah. However, some clearways are longer than 50% of the Torah. If this is the case, a pilot must not use this extra amount in his performance calculations. To summarize, a clearway is designed to be an area free from objects which may cause hazard to an aeroplane in the initial phase of flight, particularly in emergency situations. The clearway serves no other purpose and therefore may not be used as an extension to the landing area or stopping area. Having discussed the extra runway extensions of stopways and clearways, we will now focus on three more specific distances, other than the Torah, which you will need to understand. The first of these distances is the accelerate stop distance available, or ASDA. This used to be known as the emergency distance available. The accelerate stop distance available is the distance from that point on the runway at which the aeroplane can commence its takeoff run to the nearest point in the direction of takeoff, after which the aeroplane cannot be brought to rest in an emergency without the risk of accident. At most aerodromes, the ASDA will be the same length as the Torah, as illustrated here. However, if there is a stopway present, the ASDA can be increased beyond the TORA to include the stopway. Remember though, the ASDA is to be used solely for the rejected takeoff. This will be covered in detail, particularly when we deal with the medium-range jet, the Boeing 737, in the Class A section of this course. In simple terms, the ASDA is equal to the length of TORA plus the stopway if a stopway is present. The second of the specific distances that a pilot needs to understand is the takeoff distance available, normally abbreviated to TODA. The takeoff distance available is that distance from the point on the runway at which the aeroplane can commence its takeoff run to the nearest obstacle in the direction of takeoff, projecting above the surface of the aerodrome and capable of affecting the safety of the aeroplane. At most aerodromes, the TODA will be the same length as the TORA, as illustrated here. However, if there is a clearway present, the TODA can be increased beyond the TORA to include the clearway. You may recall that there was a maximum permissible length of clearway which equated to 50% of the TORA. This makes the maximum possible TODA 150% of the TORA. In simple terms, the TODA is the TORA plus the clearway, if such a clearway is present. The last of the specific distances we need to mention is the landing distance available, or LDA. The landing distance available is the length of runway which is declared available by the appropriate authority, commencing from the point on the surface of the aerodrome above which the aeroplane can commence its landing run, and extending to the nearest point in the direction of landing, beyond which the surface of the aerodrome is incapable of bearing the weight of the aeroplane under normal operating conditions. The LDA stretches from one threshold to another. There is no other distance that is allowed to be used for landing. Even stopways are not to be used. They are only to be used for an abandoned takeoff. Having learnt all the various individual distances available at an aerodrome, there is one last item to consider. A runway for which the accelerate stop distance available is equal to the takeoff distance available is considered to possess what is called a balanced field length, or more simply, a balanced field. In the case on screen, there are no stopways or clearways, but a field may also be balanced when the stopway and clearway are of equal length. In such a case, the ASDA and TODA are still the same. The term is used because many takeoff performance calculations can be simplified by using balanced field lengths. We will consider balanced fields when dealing with takeoff in the Class A section of this course. When the TODA and ASDA are not the same lengths, as in the case illustrated here, we are dealing with what is called an unbalanced field. The very last aerodrome surface consideration which we'll need to deal with is the load-bearing capability of the runway. It may seem an obvious point, but a small aerodrome, such as the one shown on screen, would not have a strong enough paved surface to bear the load of a Boeing 747. The aeroplane would simply sink into the surface, damaging the aerodrome and of course the aeroplane itself. In order to prevent aeroplanes and aerodromes suffering from such problems, a standard classification system of aerodrome and aeroplane loading was adopted by the ICAO, International Civil Aviation Organization. This classification is divided into two main parts. One part establishes pavement strength codes for all aerodromes, and the other establishes load ratings for all aeroplanes. We will deal firstly with the pavement strength codes for aerodromes. All major aerodromes have a pavement strength report, which is divided into 5 sections, as shown on screen. The first section is the Pavement Classification Number, or PCN. This value is a measure of the bearing strength of the runway, starting from 0. In our example, we have a pavement classification number of 70. So if the aeroplane's classification load is greater than this, then runway fracture may occur. The second section codes the pavement type, either rigid or flexible. The third section relates to the subgrade strength category, which can be high, medium, low, or ultra-low. The fourth section relates to maximum tire pressure. And the final section specifies the pavement evaluation method, which can be either a technical evaluation or evaluated by user assessment. The PCN coding is not important for the JAA aircraft performance exam, but a pilot really must be able to decode these reports when flying. The second part of the ICAO system deals with the aeroplane load ratings based upon certain subgrades. The load ratings are called the Aircraft Classification Number, or ACN. The values of the Aircraft Classification Number are given so that they may be compared with the Pavement Classification Number. This simple rule is that the Aircraft Classification Number is not allowed to exceed the Pavement Classification Number for the corresponding type of subgrade surface. The best way to understand how this rule works is to look at an example, such as the one shown on screen. The pavement strength report gives the pavement classification number as 30 on a flexible surface with a low strength subgrade. The pavement is medium tire pressure restricted, and the evaluation of the pavement has been carried out by technical analysis. Our example aeroplane 737 on the same low subgrade surface has an aircraft classification number of 42. The ACN can be obtained from the aeroplane flight manual, but the important point to note is that the aircraft classification number is greater than the pavement classification number. This basically means that the aeroplane is applying a far greater load to the pavement than the pavement can bear. The pavement is capable of bearing an aeroplane classification load of only 30. It would therefore not be prudent for our aeroplane to operate on this particular aerodrome. There would be a danger of the aeroplane sinking into the pavement, causing damage to the pavement and/or the aeroplane. However, there is an allowance for overload on the pavement. The pavement classification number value includes a safety factor, so that a 10% increase in aircraft classification number over the pavement classification number is generally acceptable for pavements that are well consolidated, in good condition, and provided that certain conditions are adhered to. Individual aerodrome authorities are free to permit overload operations as long as pavements remain safe for use by aircraft. If the aircraft classification number exceeds the pavement classification number by values of more than 10%, then more stringent conditions are set out and movements must be very carefully monitored. In this last part of the lesson on aerodromes, we will test the knowledge you have learnt so far in relation to runway distances. Shown here is a runway with a stopway and a clearway. Which of the labelled distances, number 1, 2, or 3, represents the takeoff run available? Click on the relevant number. Tora is represented by distance number 3. If you recall, Tora was defined as the declared length of runway, starting at the point from which an aeroplane can commence the takeoff and ending at the nearest point which is unsuitable to bear the load of the aeroplane under normal conditions. In most cases, the TORA is essentially the paved length of runway from one threshold to another, and did not include any available lengths of clearways or stopways. Using the same image, click on the relevant number which represents the takeoff distance available. TODA is represented by distance number 1. You may recall that we said TODA is the length of TORA plus any clearway available. Remember though that we cannot use any amount of clearway that is greater than 50% of the TORA. Lastly, which of the given distances is represented by the landing distance available? The landing distance available is represented by distance number 3. You may recall that the landing distance available stretches from one threshold to another. There is no other distance that is allowed to be used for landing. Even stopways are not permitted to be used. They were only to be used in the event of an abandoned takeoff. Hopefully from this lesson you will have learnt a lot more detail about the aerodrome and its available distances. These are important points, and errors in the calculation of runway distances can be catastrophic. There are many other runway characteristics that affect aeroplane performance, such as runway slope and condition, but these will be described in detail during the takeoff and landing sections of this course. Be sure to familiarize yourself with an aerodrome prior to using it, so that no surprises or embarrassing mistakes are made. You can find most of this information in the aircraft operating manual or your aerodrome plates. This section on general performance principles deals with the factors that control and determine the performance of an aeroplane throughout the different phases of its flight. We will start with the takeoff and then proceed to the climb, descent, en route, and lastly the landing phase. This first lesson deals with the takeoff. The takeoff stage of flight is defined as being from brake release until the aircraft reaches a specified height, called the screen height. The screen height varies from 50 feet for Class B aeroplanes to 35 feet for Class A aeroplanes. As the aircraft accelerates down the runway, a speed will be reached where the pilot applies back pressure on the control column to raise the nose wheel off the ground. This procedure is called rotation, and it is initiated at an indicated airspeed which is called VR. From rotation, the aeroplane pitch attitude will increase, and eventually the main wheels will lift off the runway. The speed at which they do so is called V-LOF. After this point, the aeroplane starts its initial climb, and eventually will reach the screen height. However, a specific speed needs to be gained before the screen height. This speed is called the takeoff safety speed. There is a certain minimum value associated with this speed, which is usually based upon the aeroplane's stall speed and/or its control speed, but these will be dealt with later. In large twin-engine aircraft, the takeoff safety speed is commonly referred to as V2. The takeoff can be divided into two parts. We call these the ground run and the airborne section. The first part, the ground run, is usually referred to as the takeoff roll required, or the takeoff run required, which is the distance traveled from brake release to liftoff.
The second part of the takeoff, the airborne section, is commonly referred to as the initial climb. This is the distance covered from liftoff until the aeroplane reaches the screen height. The combined length of the takeoff run required and the initial climb is known as the takeoff distance required. As pilots, we need to make sure that the takeoff distance required does not exceed the available distance at the aerodrome we are using. This can be achieved by checking those factors which affect the takeoff distance and ensuring that the performance achieved will still enable us to take off safely within the constraints of the airfield. This may seem obvious, but there are many incidents to suggest that this important consideration is often forgotten. A long takeoff distance is considered to be poor performance, whereas a short takeoff is considered to be good performance. However, in commercial transport, the performance is not measured in terms of the takeoff distance, but rather in terms of the weight that can be carried. A good performance, in terms of a commercial flight, would be a takeoff with a large weight, whereas a poor-performing aeroplane would only take off with a small weight. As a general rule, any effect that would cause the aeroplane performance to reduce would cause the aeroplane's takeoff distance to increase and/or to reduce the takeoff weight. To better understand takeoff performance, we need to fully grasp the forces acting upon an aeroplane and how these forces might change throughout the takeoff. Shown on screen is an aeroplane at rest at the brake release point. A typical 737-400 series has a maximum all-up mass of 68,000 kilograms. This mass will be accelerated from the center of gravity of the aeroplane towards the center of the Earth by gravity. The resulting downward force is called weight. The objective of the takeoff procedure is to create a sufficiently high enough force to oppose this weight and allow the aeroplane to fly. The principal force which is used to oppose weight is lift. In simple terms, to generate a lift force, we need a mass of air to pass over an aerofoil. The aerofoil in our case is the aeroplane wing. To make the air flow over the wings, the aeroplane must be pushed through the air. The faster the aeroplane travels through the air, the more lift will be created. The aim at takeoff is to gain a sufficient amount of forward speed to create enough lift to help counteract the weight, and thus allow the aeroplane to fly. However, in order to move the aeroplane through the air, there must be a horizontal forward-acting force. This forward-acting force is generated by the engines and is called thrust. With a given amount of thrust, the aeroplane will accelerate and air will flow over the wing, thereby creating lift. A detailed explanation on how propeller and jet engines produce thrust is beyond the scope of this course, but nonetheless, brief explanations will be provided at appropriate times. The basic concept of the modern jet engine is that it draws a large mass of air through its intake and accelerates it, and finally ejects it. The principle involved here is mass multiplied by acceleration produces a force. This is an adaptation of Newton's second law of motion. The greater the acceleration of air, or the greater the mass of air, the greater the thrust force produced. However, as the aeroplane travels faster, the velocity of the air entering the engine starts to match the velocity of air exiting the engine. The result of this is that the air is not being accelerated as much, and thus less thrust is produced. So, as the aeroplane speed increases, the thrust produced by the jet engine decreases. This loss of thrust with increasing forward speed is referred to as intake momentum drag. When the aeroplane reaches speeds in excess of 0.2 Mach, then the air ahead of the engine starts to compress, increasing the air density, and therefore increasing the total mass of air flowing through the engine. As a result, this helps to limit the loss of thrust caused by intake momentum drag. This thrust recovery is called ram recovery or ram effect. So initially, as speed increases, thrust will fall, but above 0.3 Mach, the thrust loss starts to reduce due to the ram effect. In the speed range used for takeoff, the jet engine aeroplane never attains sufficient speed to gain the full ram effect. Therefore, in takeoff, as the jet aeroplane accelerates down the runway, thrust will reduce. The propeller engine generates its thrust in a similar way to the jet engine. A mass of air is still accelerated rearwards, but the propeller is acting much like a wing in that it produces lift, only this time in a forward direction. You will recall that if a mass of air were to pass over an aerofoil, then lift will be produced. In order to pass air over the propeller so it can generate lift, it must be turned through the air by the engine. Shown here is a propeller in cross-section. The amount of lift produced by the propeller blade and the amount of air that is displaced backwards is a function of the angle of attack. The angle of attack is the angle between the relative airflow and the chord line of the aerofoil. The greater the angle of attack, the greater the lift force, and the greater the amount of air displaced rearwards. When the aircraft is stationary, the airflow relative to the propeller is from beneath, as shown. However, as the aeroplane gains forward speed, more of the airflow comes from the front, and as a result, the angle of attack and subsequent lift produced will decrease. So, similarly with the jet aeroplane, a propeller-driven aeroplane will experience decreasing thrust during the takeoff. There is one more force to consider. As the aeroplane accelerates down the runway, it will encounter several forms of resistance, called drag. Resistance from the air is called aerodynamic drag, and resistance from the wheels and the runway is called wheel drag. We'll deal with aerodynamic drag first. Aerodynamic drag has two forms, parasite drag and induced drag. During the takeoff, the only form of aerodynamic drag to concern us is parasite drag. Parasite drag is created by the impact of the aeroplane on the air. It follows then that as the aeroplane travels faster through the air, parasite drag, and thus the aerodynamic drag, increases. Therefore, during the takeoff, aerodynamic drag is increasing, as shown in this graph. Having discussed aerodynamic drag, let's now consider wheel drag. Wheel drag is basically the friction between the wheel and the runway, and is a function of their frictional coefficient and the load placed on the wheel. As an example of this, press your finger lightly on the desk and push your finger forwards. You will notice a resistance to the motion of your finger. Repeat this scenario, but now press down harder. You will notice much greater resistance to the motion of your finger. This example aptly demonstrates that the greater the load placed on the wheels, the greater the wheel drag. Returning to the takeoff, as more lift is generated by the airplane accelerating down the runway, there will be less load on the wheels, and thus the wheel drag will decrease. Wheel drag will eventually reduce to zero once the airplane has achieved liftoff. To summarize, aerodynamic drag increases during the takeoff, whereas the wheel drag decreases during the takeoff. As illustrated on screen, the total effect of the drag on the aeroplane is that it increases with speed, up to liftoff. Adding the thrust line onto the graph, you will recall that for either the prop or the jet aeroplane, it was stated that the thrust decreased during the takeoff. At the start of the takeoff, you can see that there is a large margin of thrust in excess of the total drag. This is shown by the blue area between the drag and the thrust lines. This excess thrust is what is used to accelerate the aeroplane. Notice, though, that as the aeroplane gains speed during the takeoff, there is less and less excess thrust available, and therefore less acceleration. Next, we'll examine what determines the takeoff distance, and also what roles the four forces play in determining the takeoff distance. In order to do this, let's briefly examine the formula that is used to calculate the takeoff distance. The letter S is the displacement or distance required from rest to reach a specified speed, which is v, with a given acceleration a. Acceleration is force divided by mass. The force is thrust minus aerodynamic drag and minus the wheel drag. Expanding the formula in this manner allows you to see how a change in one of the variables has a knock-on effect on the takeoff distance. For example, if there is a reduction in thrust, acceleration will reduce. If acceleration reduces, then the distance required to a specified speed increases. Although we have already mentioned how some of these variables change during the takeoff, we'll now analyze in detail all the forces that can affect the takeoff, with our principal concern being how these factors affect the takeoff distance. The first of the factors that affect the takeoff is the effect of mass. Increasing mass has four significant effects on the takeoff, all of which can be observed in the formula for the takeoff distance. The first is that a greater amount of mass for a given applied force will reduce the acceleration that the aeroplane can achieve. Essentially, the heavier the object, the harder it is to accelerate it. This is the effect of inertia. More mass will create more inertia. If the acceleration of the aeroplane is reduced, then the distance required for it to reach a specific speed will increase. Therefore, the takeoff distance will increase. A second effect of mass is that there will be more load on the wheels, and therefore wheel drag will increase. An increase in drag will of course reduce the acceleration of the aeroplane. And once again, if the acceleration of the aeroplane is reduced, then the distance required for it to reach a specific speed will increase. Therefore, the takeoff distance will increase. The third effect is not as apparent as the rest. A heavier aircraft will require more lift in order to get airborne. To get this extra lift, the aeroplane will need to travel faster through the air. This means that the aeroplane will need to accelerate to a higher takeoff speed before it can get airborne. Getting to this higher speed will require a greater distance, and therefore the takeoff distance will increase. The fourth effect is that a higher mass will reduce the aeroplane's initial climb angle. This decreased climb angle will increase the distance required to reach the screen height as shown, and therefore will again increase the takeoff distance. The effect that the mass has on the climb will be dealt with more comprehensively in the next lesson. In summary, the effect of increasing mass has four detrimental effects on takeoff performance. Always ensure that the aeroplane mass is within the performance limitations. Mass calculations are dealt with more comprehensively in the Mass and Balance course as part of your theoretical knowledge training. The next factor which will affect the takeoff performance is the air density. This has three effects. The first effect is that a reduced density means that there is less weight of oxygen available for combustion within the engine. There is also less mass. As a result of less combustion and less mass, the thrust produced by the engine is reduced. Reduced engine thrust will reduce the acceleration force it can produce, and, as a result, the takeoff distance will be increased. The second effect of a reduced density concerns the takeoff speed. You will recall from an earlier lesson that in order to generate sufficient lift, a mass of air needs to flow over the aeroplane wing. If the air density is reduced, then that mass of air is reduced in any given volume. Thus, to generate sufficient lift, the remaining mass must flow faster over the wing. This is achieved by accelerating the aeroplane to a higher speed. To gain this higher speed, the aeroplane will have to travel a greater distance. Therefore, with a reduction in density, the takeoff distance will increase. However, a relationship between the speeds needs to be explained at this point. Dynamic pressure is the force of the flow of air over the aeroplane. You will recall that the flow of air over the wing is exactly what is required to generate lift. This dynamic pressure needs to be maintained to provide the same amount of lift. Therefore, when density falls, in order to maintain the same dynamic pressure and thus the same lift, the speed must be increased. Indicated airspeed works in exactly the same manner as lift, because it too is a function of dynamic pressure. To achieve the same indicated airspeed as the density falls, the true speed must increase. So with the scenario of reduced density in the takeoff, the aeroplane still needs to experience the same dynamic pressure to still generate the same lift and achieve the same indicated airspeed. But now the aeroplane must travel faster through the air to achieve these parameters. Thus we have a relationship in which, when the density falls, to achieve the same indicated airspeed, the true airspeed must be higher. The third effect that density has on the takeoff is that it will reduce the angle of the initial climb, and, as already mentioned, this will increase the distance to get to the screen height. Since aeroplane performance is affected by the air density, it is important to understand and anticipate what conditions lead to changes in air density and thus aeroplane performance. Although the full explanation is outside the scope of this course, high temperatures, high altitudes, and high humidity will all decrease the density of the air, and therefore decrease the takeoff performance. A useful statement to memorize is that high, hot, and humid conditions decrease aircraft performance. The next factor that will affect the takeoff performance is the wind. The aeroplane will always get airborne once a certain value of lift, dynamic pressure, or indicated airspeed is reached. However, if there is a headwind of 20 knots, then a stationary aeroplane will already be experiencing some dynamic pressure, some lift, and an indicated airspeed of 20 knots. In the case of a headwind, then, the aircraft is already closer to its flying speed, and need not travel as fast over the surface to achieve the necessary flow of air over the wing in order to fly. This forward speed over the surface is called the ground speed. Since the aeroplane need only accelerate to a slower speed, it follows that the aeroplane will travel less distance to reach that slower ground speed. So, a headwind will reduce the ground speed for any given indicated airspeed and consequently reduce the takeoff distance. A tailwind will increase your ground speed for any given indicated airspeed, because to get the air to flow rearwards across the wing, the aeroplane must first match the speed of the wind and then move considerably faster than the wind in order to ensure enough lift is generated by the wing. Accelerating to this higher ground speed will increase the takeoff distance. The additional effect that wind will have is on the angle of the initial climb. Headwinds will tend to both increase the angle of initial climb and reduce the takeoff distance, whereas tailwinds will both reduce the angle of the initial climb and increase the takeoff distance. When examining the effects that winds will have on takeoff performance, it is recommended that you do not use the actual wind that is given, just in case that when you do actually get airborne, the wind changes, and thus your takeoff distance changes. The safety recommendation is that the takeoff planning is carried out assuming a worse situation than the one which is forecast. When calculating takeoff distances, it is recommended that you only assume no more than 50% of the headwind component and no less than 150% of the tailwind component. As an example, if the wind were reported to be a 10-knot headwind, only assume 50% of this, which is 5 knots. An important note is that there is no allowance for crosswinds and therefore no safety factor for crosswinds. Crosswinds present an additional complication because of the effect of the potential crossed controls, which would have to be applied when the wind tends to push the aeroplane off the centerline. These issues mean that aeroplanes are given maximum crosswind limits. Most performance graphs that calculate the takeoff distance have the 50% headwind and 150% tailwind recommendations already applied. The example shown here includes this. You will notice this recommendation because of the different slopes of the headwind and tailwind lines. Tailwinds have a greater effect on the distance than headwinds. This can also be seen on other graphs by looking at the scale of the headwinds and tailwinds rather than just looking at the slope. In Part 2 of the General Performance Principles takeoff lesson, you learnt about some of the factors that affect the takeoff, namely the aircraft mass, the air density, and the wind. Part 3 continues with the factors that affect the takeoff, and it starts with the effect of runway slope. The next factor that can affect the takeoff performance is the slope of the runway. Slope has an impact on the takeoff distance because of its effect on how the component of weight acts along the longitudinal axis of the aeroplane. Notice here that a stationary aircraft on a level runway has its weight acting straight downwards towards the center of the earth. However, when the aircraft is on an upslope, although the weight still acts towards the center of the earth, there is a component of weight, shown here, which acts in the direction of drag, that is, backwards along the longitudinal axis. This will reduce the acceleration of the aeroplane and therefore increase the takeoff distance. Conversely, when the aeroplane is on a downslope, the weight component now acts in the direction of thrust. This adds to the forward force, therefore it will increase the acceleration and decrease the takeoff distance. A rough calculation to help quickly quantify the effect of slope is to assume that for every 1% slope, the takeoff distance is affected by 5%, or by a factor of 1.05. A general rule for airports within the United Kingdom, there is a restriction for up to 2% slope, and most takeoff performance calculations will account for slopes only up to 2%. If, however, the runway has a slope in excess of this, then permission will need to be given by the authority for the aerodrome to operate, and the pilot will also need to demonstrate competency in using it. The slope at some airfields, particularly around southern Europe, permit takeoff and landing in only one direction. Treat these runways with extra caution and always check that the current wind velocity will still allow a safe takeoff. You can check with the aerodrome information charts about the runway slopes, such as the one shown on screen. Most takeoff graphs assume a paved, hard surface. If the condition of the runway is not like this, then the effect on the takeoff distance needs to be understood and corrections have to be applied. A lot of small airfields have grass runways. The grass will increase the drag on the wheels. This drag will reduce the aeroplane's acceleration and, as a result, increase the takeoff distance. Most takeoffs and landings that you will encounter throughout your professional career will undoubtedly be on hard, paved runways. However, these surfaces, as well as grass surfaces, may be covered by standing water, snow, slush, or ice. These contaminants may cause significant performance loss to the extent that a safe takeoff is not possible. Standing water, snow, and slush behave in a similar manner to the effect of grass in that they create additional drag as the wheels pass through them. But they also create additional drag as the spray from these substances impinges on the aeroplane. This is known as impingement drag. The greater the thickness of these substances, the greater the impingement drag, and therefore the greater the increase in the takeoff distance. In fact, there may be so much contamination on the runway that the acceleration of the aeroplane is insufficient to safely get it airborne before the runway runs out. There is potentially an even greater effect on the aeroplane from ice, water, and slush on the runway, other than the effect of the increased drag on the wheels. These substances will dramatically reduce the friction between the wheel and the runway, acting similarly to a lubricant. Whilst this may not seem too much of an issue whilst trying to get airborne, it does present an enormous problem when trying to abandon the takeoff and bring the aeroplane to a stop before the end of the runway. Because there is very little friction between the wheel and the runway surface, the wheel cannot be retarded efficiently by the brakes. Otherwise the wheel will lock, and the wheel friction with the runway will reduce even further. This is most obvious when ice is present on the runway. This part of the lesson is interactive, and it will help you to understand the relationship between the various types of contaminants, the braking effect with these contaminants, and the effect on the stopping distance. The aeroplane you see is traveling from left to right. On the right-hand side of the screen, you can select the type of surface you want to test, either dry, wet, or icy. Once you have done so, looking to the left-hand side of the screen, move the slider on the horizontal bar which is positioned underneath the 3 gauges. Moving the slider to the right increases the applied braking force. But be careful. Too much braking force will cause the wheels to lock and reduce the braking efficiency. The maximum amount of braking force you can apply will change depending on the runway contamination. When you have completed this section, just click on the forward arrow to continue with the rest of the lesson. There are other effects which runway contaminants can have on aeroplane performance, which include the possibility of a power unit failure due to water ingestion, directional control problems, and possible structural damage. It is therefore vital that the pilot be aware of the type of runway contamination, its depth, its extent, its effect on the braking, and of course its overall effect on the operation concerned. The recommendation by the United Kingdom CAA is that takeoff should not be attempted when the depth of water, wet snow, or slush is more than 15 millimeters. But check with the aeroplane flight manual in case it has a more severe restriction. The information on the contamination will be provided by the aerodrome and issued to the pilot through a report. These reports are either by SNOTAM or a runway state code. Use these reports and your aeroplane flight manual to best gauge the performance considerations. An important point to note is that there is a distinction between damp, wet, and contaminated runways. A runway is considered to be damp when there is moisture present on the surface which changes its color, but insufficient moisture to produce a reflective surface. A wet runway is one whose moisture level makes the runway appear reflective, but there are no areas of standing water in excess of 3 millimeters deep. A contaminated runway is one when there is more than 25% of the runway covered in a layer of moisture whose specific gravity is equivalent to a depth of 3 millimeters or more of water. The importance of runway contamination cannot be stressed enough, as many fatal accidents may have been avoided had due account been taken of the situation. Shown on screen is a button which you can click, which will open up a document produced by the UK CAA. This discusses the issues regarding the operations on contaminated runways. It is highly advisable you read through this safety document and fully absorb the information it contains. The next factor that can affect the takeoff performance is contamination of the airframe. This includes the effect of airframe ice and excess water. Airframe ice will accumulate as a result of icing conditions being present at the aerodrome. These conditions could have resulted from a frost, freezing precipitation, or from a snowfall. The effect of these contaminants can be significant if they are not properly removed. The first effect that they have is to disrupt the airflow over the wing. This results in an increase in drag, but, just as importantly, a reduction in the lift force. The second effect is that the contaminants will increase the weight of the aeroplane, and therefore increase the stall speed. The combination of these effects is such that the takeoff distance required will dramatically increase. Icing conditions can also lead to the jamming of the control surfaces and blockage of important instruments. So it is vital that a proper pre-flight inspection be carried out, and then subsequently the correct method of ice removal is carried out. It is compulsory by law to ensure that all aeroplanes are free from ice and free from any contamination at the commencement of takeoff. It may seem strange, but excess water on the aeroplane can lead to the same effects that ice has. In heavy rain, research has shown that lift can be reduced by as much as 30%, and drag increased by as much as 25%. This, combined with increased aircraft weight, can create a significant performance loss, and thus takeoff in heavy rain really should be avoided. Unfortunately, this advice is too often ignored. Heavy rain is usually accompanied by other potential fatal hazards. These include decreased visibility, wind shear, and microbursts. Wind shear occurs when there is a rapid change in wind speed and direction. If this occurs when the aeroplane is at or near the ground with low forward speed, then there is a considerable chance that the aeroplane will become uncontrollable and may even stall. Takeoff, when wind shear is observed or forecast, should be avoided. A microburst is a column of air descending very rapidly at speeds of up to 250 km per hour, which, upon impact with the ground, spreads out in all directions. The descending column of air may or may not be accompanied by rain. The microburst is the single most hazardous weather phenomena to aeroplanes close to the ground, when they are either in the takeoff or landing phase of flight. The microburst was only first understood in the late 1970s and, after the crash of the Delta Airlines aeroplane that killed 137 people on August 2, 1985 at Dallas-Fort Worth, significant changes in safety procedures were put in place to reduce this hazard. There is a saying amongst pilot instructors that it is far better being down here and wishing you were up there than being up there and wishing you were down here. Time pressure, passenger pressure, and commercial pressure cannot and should never come in the way of safety. Delay the takeoff if necessary, and wait for the weather to improve. The last factor to consider that affects the takeoff is the configuration of the aeroplane in terms of the flap setting. Flaps are trailing edge devices used to increase the camber of the wing and generate more lift, thereby reducing the takeoff speed. However, the use of a lot of flap will dramatically increase drag as well. Let's take a look at how different flap angles can affect the takeoff distance. With no flap, the aircraft will accelerate and then climb to the screen height, as shown. However, with some flap selected, more lift will be generated, and the aircraft will get airborne at a slower speed. This can be by as much as 10 knots. However, with flap, a small penalty is paid by the fact that the initial climb angle is shallower. Nevertheless, the overall effect is that the takeoff distance reduces. If too much flap is used, then the wing will generate more drag than lift. The result of generating more drag than lift is that the acceleration is reduced and the takeoff distance is increased compared to the acceleration achieved on a no-flap takeoff. Too much flap would also significantly reduce the angle of the initial climb and exacerbating the effect. Because of the effect of large flap angles on the takeoff distance, most aeroplanes are restricted to certain flap settings on the takeoff. For example, the 737-400 series only has 2 flap settings for takeoff, either 5 or 15 degrees. As a simple rule, increasing the takeoff flap setting will improve your takeoff performance, but it will decrease your climb performance. Familiarize yourself with your aircraft and use the flap settings laid down by the manufacturer in the aircraft manual. This completes the lesson on takeoff performance. In this lesson, you should have learnt and understood all the components affecting the takeoff, and more importantly, what determines the takeoff performance. Learn the capabilities of your aeroplane and never attempt to exceed them. Never fall prey to time pressures, which make you cut corners. Most aeroplane accidents happen in either takeoff or landing phases of flight, so always prepare for the worst. The next lesson will deal with the performance of an aeroplane in the climb.
The climb section of aircraft performance deals with the analysis of that stage of flight from takeoff to the en route or cruising altitude. There are primarily two ways in which we can judge the performance of an aircraft in the climb. Firstly, by considering the angle or gradient at which the aircraft climbs, and secondly, by looking at the rate at which it climbs. We'll examine the angle or gradient of climb first. Shown here is an aircraft in unaccelerated level flight. Notice that the forward acting force, thrust, balances the rearward acting force, drag. Therefore, the aircraft maintains a steady speed. However, when the aircraft attempts to climb, as shown here, a component of the aeroplane's weight acts backwards along the longitudinal axis in the direction of drag. This component is known as weight apparent drag. It can be calculated by multiplying the weight by the sine of the angle of the climb, gamma. You'll now notice that the magnitude of the rearward acting force is now more than that of the forward acting force. If the situation were left unchecked, the aircraft would decelerate. To maintain a steady speed along the flight path, an additional amount of thrust is therefore needed to balance the magnitude of the weight apparent drag. This is known as excess thrust. You'll notice now that the forward acting force in green matches the rearward acting forces in red, and therefore the aeroplane is able to maintain a steady speed along its new flight path. To maintain a steady climb with no loss of speed, thrust must balance not only the aerodynamic drag, but also the weight apparent drag. The larger the excess thrust available, the greater the weight apparent drag that can be balanced. In other words, the more excess thrust available, the steeper the angle at which the aeroplane is able to climb. If the aircraft only has a small amount of excess thrust available, then notice now that there is too much weight apparent drag, and that the angle will need to be reduced so that the excess thrust available balances the weight apparent drag. The excess thrust can be calculated by taking the total amount of thrust available and subtracting from it the amount that balances the aerodynamic drag. The thrust remaining is the excess thrust available. From what we've just seen, for any given weight, the angle or gradient of climb depends on the amount of excess thrust available. Here is the formula used to calculate the gradient of climb. Remember that when we subtracted total aerodynamic drag from the total thrust available, we got the excess thrust available. For any given weight of aeroplane, the greater the excess thrust available, the steeper the climb angle. The smaller the excess thrust available, the more shallow the climb angle. So, in order to maximize the aeroplane's climb angle, we need to maximize the excess thrust available. In order to discover how the aeroplane concerned can maximize its excess thrust, and therefore maximize its climb angle, it will be necessary for us to see the thrust and drag data. Let's first deal with the data for a jet aeroplane. Shown here is a typical graph of total thrust available and total drag for a jet-powered aeroplane. Excess thrust available is the amount of thrust that exceeds drag. Here, excess thrust available is represented on the graph as the area between the thrust and drag lines. You'll recall that to maximize the gradient of climb, excess thrust available must be at a maximum. This is the case where the distance between the thrust and the drag lines is the greatest, as shown here. Notice that maximum excess thrust available occurs at this speed. At any other speed, the excess thrust available is less, and therefore the achievable climb angle will be less than the maximum. The speed at which the aeroplane generates the greatest amount of excess thrust, and is therefore also capable of its greatest angle of climb, is called Vx. Vx is defined as the speed for the best angle of climb. However, in order to appreciate what value this speed represents, it's necessary to mention some other speeds at this point. There are 3 such reference speeds which are used in aeroplane performance. The first is the velocity for minimum drag, or VMD. VMD speed is found at the bottom of the drag curve, as shown here. The second reference speed is the velocity for minimum power required, or VMP. VMP is about 0.76 of VMD, as shown here. The last reference speed is found at the tangent point to the drag curve, as shown here. This reference speed value is 1.32 times the velocity of the minimum drag velocity, and thus it's referred to as 1.32 VMD. Having identified the reference speeds, the most useful point to remember is that for a jet aeroplane, the speed for the best angle of climb, Vx, occurs at VMD. Flying at VMP, or 1.32 VMD, would not generate the same value of excess thrust, and therefore would not generate as steep an angle of climb as would be achievable if the aeroplane were flying at VMD. Having discussed the concept of maximum excess thrust and the speed Vx for a jet, let's now examine these concepts as they apply to a propeller aeroplane. Shown here is a typical graph of total thrust available and total drag for a propeller-driven aeroplane. We know that excess thrust is the amount of thrust able to be developed by the engine in excess of drag, and it's represented on the graph as the area between the thrust and drag lines. You'll recall that to maximize the angle of climb, excess thrust available must be at a maximum. Excess thrust available occurs where the distance between the thrust curve and the drag curve is the greatest, as shown here. Notice that maximum excess thrust occurs at this speed. At any other speed, the excess thrust available is less, and therefore the maximum achievable climb angle is shallower. Therefore, Vx for a propeller aeroplane occurs not at VMD like the jet aeroplane, but instead at VMP. Let's now examine what factors alter the excess thrust available and therefore the angle of climb. The first of these factors to consider is the effect of weight. Shown here is an aircraft in a steady climb. If we now increase the weight of the aircraft, notice that the aeroplane will have more weight apparent drag. The forward and rearward forces are not balanced, and the aircraft will decelerate. In order to maintain speed in the climb angle will need to be reduced so that the weight apparent drag is less. Now you can see that the forces are once again balanced, but the climb angle is shallower. This effect can also be observed in the formula we use to calculate the gradient of climb. If the weight increases, then the excess thrust is divided by a larger number, and so the gradient of climb will be less steep. Weight has another effect on the angle of climb, though. An increase in weight will require an increase in lift. If lift is increased, then lift-induced drag will increase, which in turn will increase total drag. This increase in drag will reduce the excess thrust available. Notice now the present value of excess thrust is not able to balance all of the weight apparent drag. Therefore, the aeroplane climb angle must be decreased to reduce the weight apparent drag to a value that can be balanced by the present value of excess thrust. However, the effect of weight on drag is a bit more complicated. Shown here is a graph representing induced drag, parasite drag, and the total drag. You may recall that we stated that if we increase the aeroplane weight, it will require more lift. Creating more lift will increase induced drag, and as a result, the induced drag curve will move upwards. Notice, though, that the total drag curve has moved as well. In fact, it's moved slightly upwards and towards the right. It's important to remember the fact that increasing weight moves the total drag curve up and to the right. Returning to the excess thrust graphs for the propeller and jet aeroplane, it's now possible to see the effect of the movement of the total drag curve. Increasing the airplane weight moves both total drag curves up and to the right. Notice, as mentioned earlier, that there is a decrease in the excess thrust available, and therefore a decrease in the maximum achievable climb angle. However, it's important to realize that the speed for maximum excess thrust available is higher. We've seen that for both jet and propeller aeroplanes, as weight increases, the speed Vx will increase. This means that although your climb angle will decrease with a higher weight, in order to get the best possible climb angle from this deteriorated performance situation, you'll have to fly at a higher speed.
In Part 1 of the General Performance Principles Climb lesson, you learnt about the angle of climb, the best angle of climb speed, and lastly, about some of the factors that affect the climb, namely aircraft mass. In Part 2, you will continue the study of what factors affect the climb angle, starting with the effect of aircraft configuration.
The next factor that affects the climb angle is the configuration of the aircraft. By configuration, we mean whether or not the flaps and undercarriage are deployed. If the undercarriage and flaps are deployed, then parasite drag will increase. More drag means that there is less excess thrust available. Notice now that the excess thrust is not able to balance all of the weight apparent drag. Therefore, the aeroplane's climb angle must be decreased to reduce the weight apparent drag to a value that can be balanced by the excess thrust. However, the effect of the gear and flaps on drag is a bit more complicated. Shown here is a graph representing induced drag, parasite drag, and the total drag. You may recall that deploying the undercarriage mainly increases parasite drag, and as a result, the parasite drag curve will move upwards. Notice, though, that the total drag curve has moved as well. In fact, it's moved slightly upwards and towards the left. It's important to understand and remember the fact that deploying gear and flaps moves the total drag curve up and left. Returning to the excess thrust graphs for the propeller and jet aeroplanes, it's now possible to see the effect of the movement of the total drag curve. Lowering the flaps and undercarriage moves the total drag curves up and to the left. Notice that, as we mentioned earlier, there is a decrease in the excess thrust available, and therefore a decrease in the maximum achievable climb angle. However, what is important to understand is that the speed at which maximum excess thrust is available is lower. Therefore, for both jet and propeller aeroplanes, as the gear and flaps are deployed, the speed for maximum angle of climb, Vx, will decrease. This means that although your climb angle will decrease with gear and flaps deployed, in order to get the best climb angle from this deteriorated performance situation, you'll have to fly at a lower speed. It therefore seems prudent not to use flaps during the climb, so that the climb angle is as large as possible. But you may recall that flaps helped improve the overall takeoff performance. So, if you do use flap for takeoff, when it is safe to do so, remove the flap in stages. Consult your aircraft manual. The next factor that affects the climb angle is the density of the air. Density has a direct influence on the thrust produced by an engine. Decreasing density will reduce the amount of oxygen in the air available for combustion. Therefore, as density decreases, the thrust of both jet and propeller aeroplanes will decrease. Returning to the excess thrust graphs for the propeller and jet aeroplane, it's now possible to see the effect of decreasing density. Decreasing density will reduce the thrust, and therefore cause both thrust curves to move downwards. Notice that the excess thrust continually decreases, and therefore the angle of climb continually decreases. An important point to note is that Vx remains constant with changes in density. However, you will recall that when density decreased, true speeds increased. So, although the speed Vx is constant with decreasing density, the true airspeed for Vx will, of course, increase. The most notable and testable part of the effect of density on the angle of climb will be through altitude. As the altitude increases, density will decrease, and the angle of climb will steadily decrease. You'll recall from an earlier lesson that high ambient temperatures and high humidity both also decrease air density and decrease aeroplane performance. The second type of climb gradient is called the ground gradient. The ground gradient is calculated using the horizontal ground distance against the vertical distance. Unlike the air gradient, this time the start point of the ground gradient is fixed in relation to the ground. If there is a headwind, notice that the aircraft, relative to the previous path, is being pushed backwards and will cover a reduced horizontal ground distance. The result is that the climb angle increases. Therefore, headwinds will increase the ground gradient. Likewise, with a tailwind, the aircraft is being pushed forwards and will cover a far greater horizontal ground distance. The result is that the climb angle decreases. Tailwinds then will decrease the ground gradient. It's important to understand how headwinds and tailwinds affect the ground gradient, because ground gradients are used to calculate obstacle clearances. If there was an obstacle, like the one shown on screen, then if a tailwind were present, the aeroplane would not clear it. So, when making calculations to assess obstacle clearance performance, the climb gradient must be adjusted to take into account the effect of the wind. If we wish to manually correct the gradient for the effect of wind, the air gradient must be multiplied by a wind factor to obtain the ground gradient. When applying the wind factor, the formula we use is either true airspeed over true ground speed, or the true ground speed over the true airspeed. Determining which formula to use is relatively straightforward. Let's assume an air gradient of 12%, with a true airspeed of 100 knots and a headwind of 20 knots. This makes the true ground speed 80 knots, giving a wind factor of either 1.25 or 0.8. Determining which of the factors to use requires that you remember that headwinds increase the ground gradient. Therefore, the factor to use in this case is 1.25. Multiplying the air gradient of 12% by the factor 1.25 will give a ground gradient of 15%. If in the example we were given a tailwind, the air gradient would be multiplied by the wind factor, which would decrease the ground gradient. There is one additional complication. If the ground gradient is to be used for the calculation of obstacle clearances, the application of headwinds and tailwinds in the wind factor calculation must include the 50% headwind and 150% tailwind rules that you learnt about in the previous lesson. Returning to the example then, if the wind rules are applied, only 50% of the headwind should be used, meaning that only 10 knots rather than 20 knots should be used in the calculation of ground speed. This makes the true ground speed 90 knots instead of 80 knots, and the resulting wind factors are 1.11 and 0.9. Again, because it's a headwind which will make the climb angle larger, the 1.11 wind factor must be used. This makes the ground gradient 13.3%. It's important that you understand when to use the 50% and 150% wind rules. In the case of climbing, use this rule whenever you have to calculate your obstacle clearance capability. In the previous scene, you learnt how to calculate the correct ground gradients for use in obstacle clearance problems. This part of the lesson will deal with those obstacle clearance problems. Firstly, let's examine a simple formula which puts this particular type of problem into perspective. The gradient is actually a ratio of the vertical and horizontal components of the climb expressed as a percentage. Shown on screen is the formula used to calculate the gradient. Rearranging the formula allows us to also calculate the horizontal and/or the vertical components. Now let's work through an example. Following a takeoff, a light twin-engine aeroplane climbs on a 10% climb gradient. By how much will it clear a 900 meters high obstacle situated at 10,000 meters from the 50-foot clearance point? In order to find out by how much the aeroplane will clear the obstacle, it's necessary to calculate the height the aeroplane will attain after covering a horizontal distance of 10,000 meters. Using the formula at the top left-hand side of the screen, you can see that to calculate the vertical component, the gradient must be multiplied by the horizontal component. This makes the equation 10% multiplied by 10,000 meters divided by 100. The answer is 1,000 meters. This means that the aeroplane will gain a height of 1,000 meters after covering a horizontal distance of 10,000 meters with a 10% climb gradient. However, the question stated that the aeroplane was at the end of the takeoff distance, and therefore at the screen height. In order to calculate the aeroplane's height above ground level, we must add the screen height, which is approximately 15 meters. We can now calculate the clearance. The aeroplane has attained a height of 1,015 meters above ground level, and the obstacle is 900 meters above ground level. Therefore, the clearance is 115 meters. You may recall that there were two primary factors we could use to analyze the performance of the aircraft in a climb. Those factors were the angle of climb and the rate of climb. Having completed the gradient and angle of climb section, let's now focus on the rate of climb. The rate of climb is the vertical speed of an aeroplane measured in feet per minute and shown in the cockpit by the vertical speed indicator, or VSI. Another way to consider the rate of climb is to see it as the velocity of the aeroplane along a gradient. Let's assume that two identical aircraft have the same angle of climb, but the one on the right has a faster speed along the gradient. Notice that over a given time, the aeroplane on the right climbs through a higher vertical distance than the aeroplane on the left. Therefore, the aeroplane on the right has a higher rate of climb. This demonstrates that forward speed is an important factor in the rate of climb. Nevertheless, if two identical aeroplanes have the same forward speed, but the aeroplane on the right travels along a steeper angle, in a given time, the aeroplane on the right climbs through a higher vertical distance than the aeroplane on the left. Therefore, the aeroplane on the right has a higher rate of climb. This demonstrates that angle of climb is also an important factor in the rate of climb. From this simple demonstration, it can be seen that the rate of climb is a function of both angle of climb and the speed along the achieved gradient. Let's return to the formula for the gradient of climb, which is shown here. The gradient is given by the formula thrust available minus thrust required divided by weight. All that is needed now is to add the velocity function, as is shown here. This is now the formula for the rate of climb. However, there is a little more detail to explain. The velocity in this case is true airspeed. Thrust and drag are both forces. Velocity is distance over time. Force multiplied by distance gives work. Work divided by time gives power. This means that instead of thrust multiplied by velocity, the formula now contains the expression power available, and instead of thrust required multiplied by velocity, the formula now has power required multiplied by velocity. The formula now reads power available minus power required, which gives excess power, divided by weight. For any given weight, the greater the excess power available, the higher the rate of climb. Conversely, the lower the excess power available, the lower the rate of climb. In order to maximize the aeroplane's rate of climb, therefore, we need to maximize the excess power available. Shown here is a graph of power available and power required for a typical jet aeroplane. In order to provide a benchmark for the next part of the lesson, it's necessary to locate the three reference speeds we mentioned earlier in the lesson. The speed found at the bottom of the power required curve, shown here, is called the velocity for minimum power, or VMP. There was another speed, slightly faster than VMP, called VMD. This speed is the velocity for minimum drag, and it's found at the tangent to the power required curve. Lastly, the highest of the performance reference speeds is 1.32 VMD, which is located at a point beyond VMD. Having analysed the reference speeds, the object now is to locate where excess power available is maximum. The area between the two curves represents the area of excess power. The greatest amount of excess power available will be found where the distance between the curves is at a maximum, as shown here on the graph. Notice that it occurs at this speed. At any other speed, the excess power is less, and the rate of climb will be less. The speed for the best rate of climb is called Vy. For a jet aeroplane, you'll notice that this speed occurs at 1.32 VMD. Vy is the airspeed to use to climb to the cruise or en route altitude, as it will give the greatest height gain per unit time. For a typical 737-400, this speed is about 275 knots, and is usually published in the Aeroplane Flight Manual as an indicated airspeed. Shown here is a graph of power available and power required for a typical light aircraft. On the graph, the greatest amount of excess power available will be found where the distance between the curves is at a maximum, as shown here. At any other speed, the excess power is less, and the rate of climb less. As we've already learnt, Vy is the speed for the best rate of climb. For a propeller aeroplane, you'll notice that this speed occurs at VMD. It's important to remember where Vy is found for both jet and propeller aeroplanes. For example, looking at the graph, it can be seen that if a propeller aeroplane were climbing at a speed equal to VMP, and then selected a slightly higher speed, the excess power would increase, and the rate of climb would increase. It's easy to see how speed changes affect both excess power and the rate of climb when the graph is used. Be aware of what the graphs look like, so that you can use them to your advantage in test situations. Let's now examine what factors can influence the rate of climb. The first of these factors is aeroplane weight. You'll recall that an increase in weight creates more weight-apparent drag, which reduces the angle of climb. For any given airspeed, if the angle of climb reduces, then so will the rate of climb, because they are both fundamentally linked. Weight has a further effect, though, that we've already talked about. An increase in weight will require an increase in lift. Increasing lift increases induced drag, which causes the drag curve to move up and to the right. The power required curve, shown in red, is actually based upon drag. Power required is drag multiplied by velocity. So, if the drag curve moves up and to the right, so will the power required curve. This results in less excess power available, and therefore a decrease in the rate of climb. The power graphs for both jet and propeller demonstrate this. However, it's important to see that the speed for maximum excess power available is no longer what it was. It's now higher. So, with higher weight, the rate of climb is decreased, but Vy is increased. The next factor that affects the rate of climb is the configuration of the aircraft. In other words, the use of flaps and undercarriage. If the undercarriage and flaps are deployed, then the profile drag of the airplane would increase. This increases total drag, and the drag curve moves upwards and to the left. The power required curves will follow the same movement as the drag curve. Notice the reduction in excess power available as is shown by the blue double-headed arrows. You may recall that a reduction in excess power reduces the rate of climb of the aeroplane. However, the important effect here is that the speed for maximum excess power is no longer the same. It's now lower. So, with the undercarriage and/or flaps deployed, the rate of climb is decreased, and Vy is decreased. If you use flaps for takeoff, remove them in stages when you've attained a positive stable climb, ensuring that you check through the aeroplane flight manual for the correct actions for your aeroplane. As you retract the flaps, the rate of climb and the speed to attain the best rate of climb will increase, so you should accelerate to ensure you remain at Vy.
In Part 3 of the General Performance Principles Climb lesson, you learnt about the rate of climb, the best rate of climb speed, and lastly, about some of the factors that affect the rate of climb, namely aircraft mass and configuration. In Part 4, you will continue the study of what factors affect the rate of climb, starting with the effect of air density.
Density is another important factor that affects the rate of climb. However, density also affects a lot of the variables in the formula for the rate of climb. Shown here is an expanded rate of climb formula, reminding you that power available is thrust multiplied by true airspeed, and that power required is drag multiplied by true airspeed. Let's just focus on the power available for the moment. Decreased density will decrease the thrust, but it will also increase the true airspeed. The overall effect is that the thrust loss is more than the true airspeed gain, meaning overall that the power available decreases. Looking at power required, decreased density will increase the true airspeed, but will have no effect on the drag. Therefore, the power required will increase. Returning to the graph, this means that the power available curves move down and to the right, and the power required curves move up and to the right. You'll notice that there is less excess power available, and this causes a reduction in the rate of climb for both aeroplane types. This effect will be repeated any time the density falls, which can be caused either by increasing altitude, increasing temperature, or by increasing humidity. We stated previously that the true airspeed for Vy increases with decreasing density. As pilots, we fly using indicated airspeeds, and therefore it's important to understand what happens to the indicated airspeed of Vy. In order that we may understand, a further explanation is needed. Shown on screen is a graphical representation of the relationship between indicated airspeed and true airspeed with altitude. We've already stated several times that with decreasing density or increasing altitude, the true airspeed must increase in order to maintain the same indicated airspeed. This graph shows the true airspeed increasing for a constant indicated airspeed. However, returning to Vy, we stated that the true airspeed for Vy increases slightly with altitude, as density decreases. You'll notice that if the true airspeed increases slightly with altitude, the indicated airspeed will decrease. In fact, Vy will eventually reduce to become the same value as Vx. This means that Vy, expressed as indicated airspeed, is actually decreasing as altitude increases. So, in summary, reduced density decreases the indicated airspeed of Vy and decreases the rate of climb. The higher the aeroplane flies, the more the excess power available diminishes, and therefore the maximum achievable rate of climb will decrease. An altitude will be reached where the excess power available decreases to zero, as shown. Therefore, the rate of climb will also decrease to zero. This altitude is known as the absolute ceiling. The graph on screen shows the excess of power for a typical aeroplane at mean sea level. Notice Vy is the speed that gives the maximum excess power available and maximum achievable rate of climb. As altitude increases, notice that the excess power available decreases, achievable rate of climb decreases, and the indicated airspeed for Vy decreases. At its absolute ceiling, the performance of an aeroplane is so reduced that it is unable to maneuver. Therefore, absolute ceiling is a rather abstract concept for a pilot. It's more useful for a pilot to know his aeroplane's service ceiling. Service ceiling is defined by the aeroplane manufacturers and aviation authorities as the maximum altitude where the best rate of climb airspeed will still produce a positive rate of climb at a specific number of feet per minute. The recommendation is to not exceed this altitude, because above it the performance envelope of the aeroplane is very small. If the aeroplane were to climb higher, the rate of climb would fall to 0. The aeroplane will not be able to climb any higher, and the absolute ceiling would be reached. At this altitude, Vy and Vx are the same speed. To find the absolute and service ceilings of your aeroplane, consult your flight manual and operate the aeroplane below the service ceiling to help maintain sufficient performance levels. To demonstrate the effect of wind, let's return to the original concept of the rate of climb. You'll recall that it was stated that the rate of climb is a function of the gradient and the forward speed. The formula on screen demonstrates this. In the case of a headwind, the gradient increases as shown, but the forward speed is decreased. Looking at the formula, one variable has gone up, the other variable has gone down. The net result on the rate of climb is that it remains unchanged. In the case of a tailwind, the gradient decreases, but the horizontal speed increases. Again, the situation is the same. One variable decreases, but the other variable increases. The net effect is that the rate of climb remains unchanged. Looking at both the headwind and tailwind examples together shows you that both aeroplanes are gaining the same height in the same time. Therefore, we may state that winds do not affect the rate of climb of an aeroplane. The last part of this lesson will deal briefly with some of the formulae you've seen so far, and how to rearrange them to suit various scenarios and questions. This first formula is the formula for the gradient of climb. The triangle on the right is a useful tool to help you rearrange the formula for any required situation. For example, if you were asked to calculate the weight, then the formula would be the thrust minus the drag over the gradient. Or, if you needed to calculate the thrust minus the drag, in other words the excess thrust, then take the gradient and multiply it by the weight. The second formula relates mainly to obstacle clearance type questions. Earlier on you were shown a typical obstacle clearance problem, and the formula used was the one shown on screen. Again, by using the triangle it's possible to rearrange the formula. If you were required to calculate the horizontal distance, you would use the vertical distance divided by the gradient. However, you may more commonly be asked to calculate the vertical distance. The vertical distance is found by taking the gradient and multiplying it by the horizontal distance. The last formula is very similar to the previous one. Instead of vertical distance, we have vertical speed, which is the rate of climb. Instead of horizontal distance, we have horizontal speed, which is the true airspeed. If you were required to calculate the gradient, then you would use the rate of climb divided by the true airspeed. Or if you were required to calculate the true airspeed, you would take the rate of climb and divide it by the gradient. Lastly, to calculate the rate of climb, take the gradient and multiply it by the true airspeed. Using these simple triangles to help you rearrange the formula can simplify the mathematical component of the JAA performance exam, and allow you to concentrate on the more theoretical performance aspects. This completes the lesson on climb performance. Ensure that you familiarize yourself with how various factors and environmental conditions affect your climb performance in terms of both the angle and rate of climb.
This lesson on descent performance will focus mainly on the forces in the descent and what factors govern the descent. In a normal flight, the descent will occur at a point we define as the top of descent, which may be up to 200 miles before the destination aerodrome. A descent will also be required following engine failure or depressurization. In this latter situation, the descent is forced early, and it is important for the pilot to be aware of what determines the characteristics of the descent so that obstacle clearance can be maintained. There are two ways of measuring the descent performance of an aircraft, either by angle of descent, sometimes called descent range, or rate of descent, sometimes called descent endurance. Firstly, let us consider angle of descent. Shown here is an aircraft in level flight with the forward forces balancing the rearward forces. Thrust in this case is balancing drag. In order to initiate a steady descent, thrust is normally reduced. Notice that the rearward force of drag exceeds the forward force of thrust and the aircraft slows down. The value of drag that exceeds the thrust force is called excess drag. In order to balance the forces and maintain speed, the nose is lowered until the weight apparent thrust provides enough forward force to balance the excess of drag. Now the aircraft will maintain this steady descent angle at a constant speed. The forward and rearward forces are in balance once again. Notice that the drag force is being balanced by both the engine thrust and the weight apparent thrust. The weight apparent thrust can be calculated by multiplying weight by the sine of the angle gamma. If thrust were reduced even more, then there would be a greater amount of excess drag. More weight apparent thrust is therefore needed to balance the greater amount of excess drag. To gain more weight apparent thrust, the aeroplane nose must be lowered even more. The result is an increase in the descent angle. For the purpose of the examinations, lowering the nose is also described as decreasing the pitch angle. From this demonstration, it is clear that it is the excess drag which determines the angle of descent. Notice that the angle gamma is the same angle as the angle of descent. Rearranging the formula on screen so that angle gamma can be calculated gives us the formula for the angle or gradient of descent. Drag minus thrust will give excess drag. In summary then, the angle or gradient of descent is controlled by the excess drag. In order to visualize this excess drag, it is necessary to return to the thrust and drag graphs that were used in the climbing lesson. Shown on screen are the thrust and drag curves for a jet and propeller aeroplane. We have learnt that in order to descend, there has to be an excess of drag. On the graphs, excess drag can be found by taking the area beneath the drag curve and subtracting from it the area beneath the thrust curve. The highlighted areas represent excess drag. Notice that if thrust is reduced at any given speed, then excess drag increases. Therefore, the descent angle increases, just as was shown on the forces diagram. If it were a performance priority to maximize the angle of descent, then from the theory we have seen so far, we would have to maximize excess drag. If thrust is reduced to 0, notice that the excess drag area is a maximum, but to obtain the maximum excess drag, the aeroplane needs to be accelerated to a very high speed, as shown. This can be achieved by closing the throttles and continuously lowering the nose of the aeroplane so as to cause the increasing amount of weight apparent thrust to accelerate the aeroplane. As speed rises even more, both the excess drag and the angle of descent will increase. The angle of descent, then, is a function of excess drag. The greater the excess drag, the steeper the angle of descent. This angle can be increased even more if it were possible to increase the excess drag. This can be achieved by deploying drag devices such as the speed brakes and the undercarriage, but attention must be paid to their maximum deployment speeds. The practical side of increasing drag to increase your descent angle occurs mainly in training and occasionally in commercial operations after air traffic reroutes. Take note that any increase in excess drag, either by deploying flaps or undercarriage, or by reducing thrust, will steepen the angle of descent. You have just learnt that to maximise the descent angle, excess drag must be maximised. In this part of the lesson, you will learn how to minimise the descent angle. Following an engine failure, the aim is to ensure that the aeroplane will cover the greatest horizontal distance so that the pilot has a large area in which to select a suitable landing field. This can only be achieved by using the flattest possible angle of descent, sometimes referred to as the minimum glide angle. To understand how this can be achieved, let us return to the aircraft in straight and level flight. If the engines were to fail, then to balance the excess of drag, which in this case will be the entire drag force, the aeroplane's nose must be lowered by a sufficient amount to create enough weight apparent thrust to balance the excess drag. The aeroplane will now maintain a steady speed in the glide. If drag were to be decreased, then notice that weight apparent thrust can be decreased by raising the nose by an appropriate margin in order to decrease the angle of glide. From this you can see that if drag were reduced to a minimum, the angle of glide will also be reduced to a minimum. This can also be seen in the graphs. Notice that VMD is the speed found at the bottom of the drag curve. At VMD, drag is at a minimum. Therefore, to descend at the minimum possible angle, the aeroplane must be flown at VMD. Shown here is an interactive demonstration allowing you to change the value of drag and observe the effect on the angle of descent and subsequent descent range. Move the drag slider on the right of the screen to observe the effects. Once you have finished, click on the flashing arrow to continue. One of the other ways to examine glide performance is to consider the aeroplane's lift-over-drag ratio, commonly referred to as the lift-drag ratio. However, before we do this, there is a little more detail on the forces diagram to discuss first. Notice that in the glide descent, the resultant of drag and lift balances the force of weight. From your Principles of Flight lessons, the term for the resultant of lift and drag is total reaction. If the drag force line is moved upwards, you can see that we now have a triangle of forces, with the angle gamma being the angle between the lift and total reaction. From the bigger picture, which shows the aeroplane's glide angle with respect to the ground assuming no wind, it is easy to prove geometrically that the angle gamma is the same as the angle between the aeroplane's glide path and the ground. Consequently, from the triangle of forces, it is clear that if there were any change in the lift and or drag values, both the angle gamma and the glide angle would change. A typical modern jet has a maximum lift-drag ratio of about 19. Where this ratio reaches its maximum value, the angle gamma will be at minimum. The lift-drag ratio reaches its maximum value at 4 degrees angle of attack and at the speed VMD. Therefore, VMD is the speed for the minimum angle of descent or the minimum glide angle. VMD is also known as a speed for LD max. The angle of attack at VMD is fixed at 4 degrees. If the angle of attack is greater or less than 4 degrees, the speed will change, the lift-drag ratio will decrease in value, and consequently the angle of glide will increase. If, following an engine failure, you fly at VMD, your aeroplane will be flying at the flattest possible glide angle. Never try to stretch the glide by raising the nose of the aeroplane. If you do so, the speed will decrease and the glide angle will steepen. At any speed other than VMD, your glide angle will be steeper than the optimal glide angle. Shown on screen is the angle of glide at VMD. The temptation is to raise the nose a little. This gives an impression from the cockpit that the glide is being extended. Looking at the diagram, if the nose were raised, the weight apparent thrust would decrease and the aeroplane would slow down. As a result, the aeroplane would not be flying at VMD and therefore not have the best lift-drag ratio. The result would be a steeper descent angle despite the fact that the aeroplane had a slightly higher nose attitude. Be disciplined in following the procedures for flying at the optimum glide angle as laid down by the manufacturers or the operator in the aeroplane flight manual. You may recall we mentioned at the beginning of the lesson that there were two ways of assessing the descent performance. We have covered the angle of descent, or descent range. Now let us consider the rate of descent, or descent endurance. You have already learnt in an earlier lesson that the rate of climb was a function of both climb angle and velocity. Similarly, the rate of descent is a function of descent angle and velocity. Shown here is the angle or gradient of descent formula that you have already learnt. All that is needed is to add the velocity function as shown. This is now the formula for the rate of descent. You may recall that force and velocity gave us power. So the correct formula for the rate of descent is the one shown. The rate of descent is equal to the power required minus the power available divided by the weight. Power required minus power available gives excess power required. So for any given weight, the rate of descent is determined by the excess power required. The greater the excess power required, the larger the achievable rate of descent. Conversely, the lesser the excess power required, the smaller will be the rate of descent. In an emergency descent, for instance a descent initiated by the pilot following depressurization, the aim is to reach flight level 100 as soon as possible. The regulations state that flight level 100 must be reached within 10 minutes. To achieve this requirement, the aeroplane would need to lose height with the maximum possible rate of descent, which can only happen if the aeroplane has maximum excess power required. Shown here are the power required and power available curves for both the jet and propeller aeroplane. The areas beneath the power required curves but above the power available curves represent the excess power required and are highlighted in light blue. In order to create the conditions of the greatest excess of power required, power available must be reduced to nil, as shown here. Notice that the blue areas of excess power required are now as large as possible. In order to achieve the greatest rate of descent, the aeroplane needs to fly at a speed that achieves the greatest excess power required. It is obvious from the graph that this can only be achieved at very high speeds. Remember that power required is a function of speed and drag. Therefore, the aeroplane needs to be configured for high drag and high speed in order to achieve maximum power required. In fact, for a lot of Class A aeroplanes, emergency descents are flown at maximum operating speeds with air brakes or speed brakes deployed and thrust at idle. If it were the aim to descend at the lowest rate of descent, the aeroplane would need to fly at a speed that gives the minimum excess power required. On the graphs, this point is plain to see. In fact, it is found at the very bottom of the power required curve. You may recall that this speed is called VMP. So to lose height at the slowest possible rate of descent, the aeroplane would need to fly at VMP. The lowest rate of descent is also known as maximum descent endurance, which essentially means the aeroplane will take the greatest time to descend. Let us now examine what factors will affect and modify the angle and rate of descent. The first of these factors is weight. For the moment, let us assume a normal descent at zero thrust whilst maintaining a standard scheduled descent speed. Looking at the diagram, a heavier aeroplane will have a greater weight apparent thrust. This creates more forward force than rearward force, and the aeroplane would accelerate. Therefore, in order to maintain the same speed and to provide extra lift to balance the weight, the aeroplane's nose must be raised. This increases the angle of attack and therefore the lift, but it also keeps the forward force of weight apparent thrust the same as the excess drag. Therefore, a constant speed is maintained but at a shallower angle. So under normal conditions, at a constant speed, An increase in weight decreases the angle of descent and therefore decreases the rate of descent. However, descent profiles are complicated as some aeroplanes, namely Class A aeroplanes, change their speed characteristics constantly during the descent profile. However, let us now consider the effect of weight on the minimum angle of descent or shallowest glide angle. You may recall that in order to achieve the minimum angle of descent, the aeroplane needs to fly at VMD, which gives the best lift-drag ratio and an angle of attack for 4 degrees. If mass is increased, VMD is increased. Therefore, our heavier aeroplane needs to fly faster to attain VMD. This concept will be shown through this next sequence. A heavier aeroplane will have a greater magnitude of weight apparent thrust. If left unchecked, the aeroplane will accelerate to a higher speed. As the speed increases, lift force will increase, but so will the drag force. Eventually, there will be enough total reaction to balance weight and enough drag to balance weight apparent thrust. At this point, the forces are balanced and a new higher steady speed is attained. This new higher speed is still VMD and the angle of attack is still 4 degrees. As you can see, the angle of descent has remained constant throughout. You may recall that increases in weight cause both the drag and power required curves to move up and to the right. Remember that this has the effect of increasing the speeds. Therefore, with higher weights, VMD, the speed for minimum angle of descent, and VMP, the speed for minimum rate of descent, will both increase. In summary, therefore, weight has no effect on the minimum angle of descent, but it will increase the speed along that descent gradient, and therefore it will increase the rate of descent. The next factor to affect the angle and rate of descent is the aeroplane's configuration. Looking at the diagram on screen, if the flaps or undercarriage were deployed, then excess drag would increase. To balance this increase in excess drag, the nose must be lowered. This action increases weight apparent thrust and a balance of forces is restored, but more importantly, the balance is achieved at a higher angle of descent and therefore a higher rate of descent. The effect of configuration can also be seen using graphs. Shown here are the drag curves for the jet and propeller aeroplane with excess drag shown by the light blue area. With flaps and undercarriage deployed, you will recall that the curves move up and left. This has the effect of increasing the excess drag and therefore increasing the angle of descent for any given speed. Notice too that the speed for the minimum angle of descent, VMD, is lower. The same effect can be seen when examining the rate of descent and by using the power required graphs. Similarly, the light blue area represents excess power required. With flaps and undercarriage deployed, you will recall that the power curves move up and left. This has the effect of increasing the excess power required and therefore increasing the rate of descent. Notice too that the speed for the minimum rate of descent, VMP, is lower. In summary then, with gear and flaps deployed, the angle and rate of descent increase, but the speeds for minimum angle and minimum rate of descent decrease. The last factor to affect the angle and rate of descent is wind. The diagram shows a descent angle and descent range with no wind. If there is a headwind blowing, the aircraft will move backwards relative to the no-wind diagram. This steepens the glide angle and decreases the descent range. However, notice that the aeroplane reaches the same descent altitude in the same time as the aeroplane flying in zero-wind conditions. This demonstrates that a headwind, which steepens the angle of descent, has no effect on the rate of descent. Conversely, if there was a tailwind blowing, the aircraft will move forwards relative to the no-wind diagram. This flattens the glide angle and increases the descent range. However, notice that the aeroplane reaches the same descent altitude in the same time as the aeroplane flying in zero-wind conditions. This demonstrates that a tailwind which flattens the angle of descent has no effect on the rate of descent. The effect of the wind on the angle of descent can be examined a little further. Because of the adverse effect of the headwind on the angle of descent, then in a glide, it would be of a benefit to increase the aeroplane's forward speed slightly. This has the effect of reducing the time spent in the headwind. This means that the aeroplane will not be pushed back as much by the wind. Similarly, with a tailwind, because a tailwind benefits the glide by decreasing the glide angle, it would be better to try and stay in this situation for longer. So this time the aeroplane's forward speed can be decreased so that the aeroplane can stay under the tailwind effect for longer and therefore be pushed further forwards. When flying on a training sortie, make sure you know the wind speed and direction, both for the surface and aloft. This will help you plan a better descent, giving you more accurate circuit patterns. But more importantly, knowledge of what the wind is doing will ensure you obtain maximum descent performance if an engine failure should occur. This completes the lesson on the general principles of descent. In this lesson you should have learnt the difference between angle of descent and rate of descent and the factors that determine them. Whilst most descents will start at a scheduled predetermined point called top of descent, and they will be uneventful, there will certainly be occasions when a pilot is rerouted and in the worst case suffer an engine failure. Under these circumstances, your knowledge of descent performance will be vital to ensure you carry out the correct actions and clear obstacles during the descent. More detail on the descent performance of different aeroplanes and the regulations that apply to these aeroplanes in the descent will be covered later.
In this lesson, we will concentrate on the general performance principles of an aeroplane in the en route phase of flight. Performance in the en route phase can be measured using the aeroplane's range and endurance parameters. These will be discussed in detail later on in the lesson. Let us firstly examine the forces acting on an aircraft in the cruise. These forces are split into couples. The first of these couples is produced by lift and weight. Weight acts through the center of gravity of the aeroplane directly towards the center of the Earth. Lift balances weight and acts through the center of pressure shown here. The effect of this couple on the aeroplane is to cause a nose-down pitching moment. The lift-weight couple is comparatively strong and thus the nose-down pitching moment is large. As an example of the size of these forces, in a 737-800 series, the maximum structural mass is 79,000 kilograms. At this mass, the aeroplane weighs around 770,000 newtons. Obviously, this weight will be balanced in cruising flight by an equal and opposite lift force of 770,000 newtons. The second couple acting upon an aeroplane in flight is that produced by the forces of thrust and drag. The effect of this couple is to cause a nose-up pitching moment. Notice, though, that this couple is far weaker than the lift-weight couple. The maximum thrust produced by the engines of a 737-800 is only 214,000 newtons. This means that the nose-up pitching moment does not balance the stronger nose-down pitching moment of the lift-weight couple. As a result, there is still a nose-down tendency. In order to maintain level flight, we need somehow to generate an opposite moment which will balance the residual nose-down pitching tendency. This is achieved by the tail plane, or horizontal stabilizer, on the aeroplane's tail assembly. The horizontal stabilizer, or tail plane, must be set at an angle which will cause a nose-up pitching moment to balance the aeroplane, or, more commonly expressed, to trim the aeroplane. Notice that now the nose-up and nose-down pitching moments are in balance and level flight is possible. The downforce generated at the tail is called tail plane downforce or tail load. Although such a force is necessary for level flight, it does have two adverse effects on aircraft performance. Firstly, notice that the tail plane downforce acts in the same direction as weight. It therefore increases the effective weight of the aircraft. The second adverse effect of the tailplane downforce is its contribution to drag. The tailplane is an aerodynamic surface designed to produce lift. It will, therefore, produce induced drag as well as parasite drag. Therefore, the greater the amount of balancing force produced by the tailplane, the greater the aeroplane aerodynamic drag. We will shortly understand that the two additional forces provided by the tailplane are detrimental to the aeroplane's en route performance in terms of range and endurance. To some extent, the amount of tailplane downforce required for level flight can be manipulated by changing the center of gravity. In flight, this can be done in one of two ways. Firstly, by selective fuel consumption, or secondly, by fuel transfer. Consuming fuel in the tail first, or transferring fuel out of the tail to other tanks, will move the center of gravity position forwards. Conversely, using fuel in the center or forward tanks first, or transferring fuel out of these tanks will cause the center of gravity to move aft. If the center of gravity moves forwards, the magnitude of the lift-weight couple increases because the arm of the two forces is now longer. This increases the nose-down pitching moment. To balance the nose-down pitching moment and maintain level flight, more tailplane downforce is needed. You may recall that this had the effect of increasing the weight and drag of the aeroplane, which would have a detrimental effect on the aircraft's performance, reducing both its range and endurance. If the center of gravity moves aft, the strength of the lift-weight couple is decreased because the arm of the two forces is now shorter. This decreases the nose-down pitching moment. To balance nose-down pitching moment, less tailplane downforce is needed to maintain level flight. Reducing tailplane downforce reduces drag and effective weight, which will increase both the aeroplane's range and endurance capability. Remember that, before you fly, when carrying out a weight and balance check, also ensure that the center of gravity is still within the limits published in the aircraft manual. Be extra careful when handling data produced by countries whose units of measurement are different to those you are used to. This particular section of the lesson will deal with the aeroplane's speed, including maximum speed, minimum speed, and the relationship between the various expressions of speed such as indicated airspeed, calibrated airspeed, true airspeed, true ground speed, and Mach number. Firstly, let us examine what we mean by an aeroplane's maximum speed. You will have learnt from earlier lessons that an aeroplane will remain at a constant speed when the forward and rearward forces are balanced, as shown here. In this case, thrust is equal to drag. In order for the aeroplane to accelerate, thrust must exceed drag. This can be achieved by the pilot opening the throttle further to increase power. With thrust greater than drag, the airplane will accelerate. As the airplane accelerates, drag will increase. When drag reaches a value which is the same as the thrust, then acceleration will cease and the airplane will have achieved balanced flight once more, but now at a higher speed. Therefore, the highest level flight speed that can be flown by the airplane will be at a speed where thrust is maximum and drag is maximum. Shown on screen are the thrust and drag curves for a typical jet airplane. Let us look again at what we have just learnt, but this time using the graphs. Here, thrust is more than drag, and therefore in level flight, the airplane will accelerate. As we explained, drag will increase as speed increases until thrust and drag are again equal. This speed is the fastest speed the airplane can achieve in level flight. Look at the graph again and notice that there is another point on the curves where thrust and drag are equal. This speed represents the slowest speed that can be maintained at a given thrust setting, since thrust and drag are equal. In level flight, it would be impossible to fly any slower at this thrust setting since the rearward force of drag would exceed the force of thrust. The area to the left-hand side of the bottom of the drag curve is commonly referred to as the back of the drag curve, or the speed region of reversed command. Flying at these speeds is inefficient and not recommended since a lot of thrust is needed to maintain a fairly slow speed. Notice that at high altitude, the thrust produced by the engine decreases. Looking at the graph now, it is clear to see that at high altitude, the maximum achievable level flight speed is slower, and the minimum achievable level flight speed is faster than at lower altitudes. Thus the range of speeds for the airplane is narrower. This next part of the lesson will focus on the explanation of the various expressions of aeroplane speed. Different expressions of aeroplane speed are used for different purposes depending on whether we are concerned with aerodynamics, operations, navigation, or even performance. In most cases, aeroplane speed is measured using certain types of probes, called the total pressure and static pressure probes, as shown here. These probes help us to isolate dynamic pressure on which indicated airspeed is based. You can feel total pressure by simply putting your arm out of the window of a moving car. However, total pressure probes, sometimes called pitot probes, and static probes suffer from errors. Without any correction to the errors, the speed which is obtained from the probes when dynamic pressure is being sensed is called the indicated airspeed, abbreviated to IAS. Indicated airspeed is the speed that is displayed on the airspeed indicator. If the pressure probes are corrected for instrument and position errors, the speed is called calibrated airspeed, abbreviated to CAS. This speed is also known as rectified airspeed, or RAS, but this expression will not be used on this CD. Calibrated airspeed is more accurate than indicated airspeed. In large, modern commercial airplanes, the air data computer automatically corrects the pressure probe data for these errors and displays the calibrated airspeed in the airspeed indicator rather than the indicated airspeed. The final correction to make to the information received from the pressure probes is the correction to compensate for the effect of compressibility. Typically, at speeds beyond 220 knots, the air ahead of the airplane does not move out of the way. As a result, the air starts to build up and compress in front of the airplane. This build-up of air has an effect called the compressibility effect. If the probes are corrected for the compressibility error, as well as position and instrument errors, the speed obtained is called equivalent airspeed, abbreviated to EAS. Equivalent airspeed is the most accurate of the speeds which are obtained from dynamic pressure. For the most part, this performance CD will assume that indicated airspeed, calibrated airspeed, and equivalent airspeed are the same. The next speed to consider is true airspeed, abbreviated to TAS. True airspeed is the equivalent airspeed corrected for density error, and as the name suggests, is the true speed of the aircraft relative to the air through which the aeroplane is flying. On screen is a very simplified formula showing that true airspeed is proportional to the equivalent airspeed and inversely proportional to the density. If, for a constant equivalent airspeed, the density were to fall, the true airspeed would increase. This means that with increasing altitude at a constant equivalent airspeed, true airspeed increases, as shown by this graph. True airspeed can be calculated by using the tables in the aeroplane flight manual, using a flight navigation computer, or even using the airspeed indicator. True airspeed is mainly used for navigation and flight planning purposes. The next speed to consider is the true ground speed, abbreviated to TGS or just GS. This represents the aeroplane's speed within a fixed ground reference system. Put more simply, it is the aeroplane's velocity over the ground. The true ground speed is equal to the true airspeed plus the wind component. If there is a tailwind, then the aeroplane's speed over the ground will increase by a value equal to the speed of the tailwind. So, in our example, if the true airspeed is 250 knots and the tailwind is 20 knots, the true ground speed is 270 knots. Conversely, if there is a headwind, the aircraft's speed over the ground will be reduced by a value equal to the speed of the headwind. So, in our example, if the true airspeed is 250 knots and the headwind is 30 knots, the true ground speed is 220 knots. If the headwind or tailwind components are not already known, these can be worked out using a flight navigation computer or by using the supplied CAP 698 manual on page 49, as illustrated here. At speeds higher than about 220 knots, some of the energy of the aeroplane goes into compressing the air ahead of the airplane and locally increasing the density of the air. Compressibility affects the amount of drag force on the aeroplane, and the effect becomes more important as speed increases. As the aeroplane moves through the air, it makes noise simply by disturbing the air. This noise emanates outwards in the form of pressure waves. These pressure waves stream out away from the aircraft at the speed of sound in all directions, acting just like the ripples through water when a stone is dropped in the middle of a still pond. However, as the aeroplane approaches the speed of sound, it actually starts catching up with its own pressure waves in front of it. These pressure waves turn into one big pressure shock wave, which causes a loud big bang, called a sonic boom. The shock wave generated actually buffets the aeroplane and decreases the lift force. Obviously, because of the increasing drag, decreasing lift, and aeroplane buffet, pilots need to know when they are approaching the speed of sound. Shown here is a picture of an aeroplane passing through the speed of sound. The shock wave actually causes condensation, which allows an observer to actually see the pressure wave. These two pictures show the shock waves on military aeroplanes flying at 3 times the speed of sound. The next scene will discuss a specific aeroplane's speed which allows pilots to know when they are approaching the speed of sound. On screen is the animated demonstration you saw earlier, but this time you can adjust the aeroplane's speed using the slider at the bottom. When you have finished, just click on the flashing forward arrow. The ratio of the speed of the aeroplane to the speed of sound in the air determines the magnitude and intensity of many of the effects of high-speed flight. Because of the importance of this speed ratio, aerodynamicists have given it a special name called the Mach number in honor of Ernst Mach, a late 19th century physicist who studied gas dynamics. Mach number is not an actual speed as such. It is, as we have already said, the ratio of the true speed of the aeroplane to the local speed of sound. Mach number is best illustrated using an example. To calculate the Mach number, simply divide the true airspeed by the local speed of sound. At sea level in ICAO conditions, the local speed of sound is 661 knots. If the true airspeed of the airplane is 510 knots, then using the formula on screen, the Mach number is 0.77. In other words, the airplane is travelling at about 3/4 of the speed of sound. If the airplane were to fly faster, the Mach number would increase. If the airplane accelerated to 661 knots, then its speed would be equal to the speed of sound and the airplane would be at Mach 1. Airplanes flying between about 0.8 Mach and 1.2 Mach are said to be in transonic flight. However, the term supersonic is more commonly known. Supersonic flight describes flight speed above Mach 1.2. The speed of sound varies with temperature. As altitude increases, the reducing temperature causes the local speed of sound to fall. At 30,000 feet, the speed of sound is 590 knots. If the true airspeed of the airplane is kept constant at 510 knots, as a result of the falling local speed of sound with altitude, the Mach number will increase. As the aeroplane's speed approaches Mach 1, the compressibility and approaching shockwave can have very detrimental effects on the aeroplane's performance if the aeroplane is not designed to mitigate such effects. As a result, most commercial aeroplanes in service today have a limit on the maximum Mach number they are allowed to fly at. This maximum operating Mach number is called MMO. The Mach number of an aeroplane can be displayed in a number of places in a typical cockpit. Shown here are just a few of these places. Having discussed all the relevant speeds of an aeroplane, it is important to understand the relationship of these speeds with one another as altitude changes. This is best illustrated on a graph. The y-axis is altitude and the x-axis is aeroplane speed. If calibrated airspeed, or simply indicated airspeed, is kept constant with altitude, then as density falls, the true airspeed will increase as shown. But if true airspeed increases with altitude, while the local speed of sound decreases, then the Mach number must increase. These lines representing these three speeds can be manipulated to help solve complex problems. If the true airspeed were to be kept constant with altitude, the TAS line would be drawn vertically and the CAS and Mach lines as shown. Now, calibrated airspeed decreases whilst Mach number increases. If Mach number were to be kept constant, the diagram could be drawn so that the Mach line is straight up. Notice that TAS and CAS decrease with altitude. The same can be done with decreasing altitude. If the CAS is kept constant during the descent, keep the CAS line vertical and notice that the TAS and Mach number lines slope as shown. This means that if CAS is constant during a descent, the TAS and Mach number will decrease. To help you remember how to draw the lines, C, T and M always appear from left to right. You can use Britain's favourite food, chicken tikka masala, as an acronym for remembering C, T and M. The next section of this lesson analyses the two cruise performance parameters, range and endurance. When flying for range, we are asking the question, how much fuel will the aeroplane use per unit distance? When flying for endurance, we are asking the question, how much fuel does the aeroplane use per unit time? Let us firstly deal with the endurance of the aeroplane. The endurance of an aeroplane is the time it can remain airborne on a given quantity of fuel, or, put another way, endurance can be expressed as fuel used over a given airborne time. The only time an aeroplane will be flown by the pilot for maximum endurance is when the aeroplane is in a holding pattern over its destination. For instance, when there are long landing delays. In this situation, running out of fuel starts to become a problem. In this lesson, we will define endurance to be the ratio airborne time over fuel used for that time. However, to use this formula, a small adjustment needs to be made, as shown here. This now becomes the formula for specific endurance. The units of specific endurance are airborne hours per kilogram of fuel consumed. The endurance of an aeroplane is simply a function of its fuel flow or fuel consumption as shown by the formula. An aeroplane which can minimize its fuel flow will achieve maximum endurance. Therefore, when analyzing the maximum endurance capability of an aeroplane, it is necessary to understand what controls the fuel flow. You should note that this parameter is different for a jet and propeller aeroplane. Let us examine the jet aeroplane first. Here, fuel flow is a function of the fuel used per unit of thrust, multiplied by the total number of thrust units. Obviously, if it were possible to reduce the fuel used per unit of thrust and the total number of thrust units required, then the total fuel flow would be reduced. Fuel used per unit thrust is most commonly known as specific fuel consumption, which is abbreviated to SFC. This value needs to be small. In other words, the aim is to reduce the amount of fuel used to produce each thrust unit. For a jet engine, this occurs when ambient temperature is very low and engine RPM is very high. This can only occur at high altitude. So, flying at high altitude minimizes the fuel used per unit of thrust. Having minimized the fuel used to produce each unit of thrust, the aim is now to fly the aeroplane using minimum possible total thrust because each unit of thrust requires fuel to be consumed. This problem is comparatively simple to solve. In level flight, the forward-acting force of thrust is controlled and balanced by the rearward-acting force of drag. If drag is small, the airplane need fly with only a small amount of thrust. Looking at the formula then, thrust can be replaced by drag since the value of drag is equal and opposite to the value of thrust. To minimize drag, the jet airplane simply flies at the velocity for minimum drag. Therefore, VMD is the speed to fly for maximum endurance. In summary then, for a jet airplane to maximize its endurance by minimizing its fuel flow, the pilot would fly the airplane at VMD and fly as high as possible. The situation with endurance and fuel flow for a propeller airplane is very similar to that for the jet airplane. There is just one small difference in the formula we use. Turboprop and piston engines first convert chemical energy in the fuel into power output on a shaft. The propeller then converts that power into thrust. So, whereas for a jet the formula for fuel flow was fuel used per unit thrust multiplied by the total number of thrust units, for a propeller the formula is fuel used per unit of power multiplied by the total units of power. Obviously, to minimize the fuel flow, the fuel used per unit of power and the total number of power units developed must be kept to a minimum. Fuel used per unit power, as you already know, is called specific fuel consumption. This value needs to be small, but for the majority of propeller aeroplanes the value is more or less fixed. However, in very general terms, it is safe to say that for piston engines, specific fuel consumption is a minimum at lower altitudes, whereas for turbopropeller engines, specific fuel consumption is a minimum at middle to high altitudes. Therefore, the only other way to minimize fuel flow is to use the minimum amount of power. This can be achieved by flying at the speed for minimum power required, or VMP. Note that for a propeller aeroplane, it is VMP that is the speed for maximum endurance, whereas for a jet, it is VMD. Having studied how to achieve maximum endurance for both jet and propeller engines, let us now examine what factors actually affect endurance. The first factor we must discuss is the effect of weight. You will recall that increasing the weight of the aeroplane increases induced drag and thus moves the total drag curve and power required curves up and right. Looking at the jet diagram which uses drag, you can see that at higher weights, the aeroplane has more drag and therefore requires more fuel flow. In this situation, the endurance will decrease. We must also note that the speed for maximum endurance, VMD, is now higher. For a propeller aeroplane, the situation is similar. For a propeller aeroplane at higher weights, more power is required, therefore, fuel flow increases and endurance decreases, but also the speed for best endurance, VMP, is higher. There is one other effect that is seldom mentioned. At higher weights, operating altitudes are lower, which for a jet airplane means that the specific fuel consumption increases because at lower altitudes the jet engine is less efficient. The next factor which affects endurance is the aeroplane's configuration. While it seems an obvious point that the undercarriage and/or flaps should not be deployed in the cruise, There will be occasions when a pilot will find himself stacked with other aeroplanes in a holding pattern over the destination airfield. As the aeroplane at the lowest level exits the hold to land, the other aeroplanes will have to descend to a lower hold and eventually prepare for the landing by deploying undercarriage and flaps. You will recall that deploying the flaps and undercarriage increases parasite drag and thus causes the total drag curve and power required curve to move up and left. Looking at the jet diagram, which uses the drag curve, you can see that with the gear and flaps deployed, the aeroplane has more drag and therefore requires greater fuel flow. But notice that the speed for maximum endurance, VMD, is now lower. For a propeller aeroplane, it is much the same. With gear and flaps deployed, more power is required. Therefore, fuel flow increases and endurance decreases, but also the speed for best endurance, VMP, is lower. Fuel flow in the landing configuration can increase by 150% compared to a clean configuration, so it is important not to deploy gear or flaps too early and unnecessarily increase the fuel costs for the flight. What other factors affect endurance? We still haven't considered altitude or wind. Well, the case of wind is quite simple. It has no effect on endurance. You will remember that maximum endurance is concerned with minimizing fuel flow. Now, it should be obvious that wind does not affect the fuel flow into the engine. Endurance is about time in the air, not distance covered. Whatever the effect of wind on range, an aeroplane will still remain airborne only for as long as it has usable fuel in its tanks. Altitude, however, does affect endurance. Its effect, though, is a little complicated and is very dependent on engine type. Generally, jet aeroplanes become more efficient as altitude increases, partly due to the decreasing ambient temperature, but also because of the increasing RPM required to maintain thrust. Therefore, theoretically, the maximum endurance of a jet aeroplane will be achieved when flying at or above the tropopause, where the ambient air temperature is lowest. Turbopropeller aeroplanes function in a similar way to a jet, since they are, in essence, jet engines with a propeller attached to a geared shaft. However, even though the turbopropeller engine gains efficiency with altitude, the power required increases, offsetting the efficiency gains. This means that for the majority of modern turbopropeller aeroplanes, maximum endurance is achieved at around 10,000 feet or less. Piston engine aeroplanes are most efficient at sea level when the manifold pressure is high and RPM is low, provided that the mixture has been leaned correctly. In summary then, jet aeroplanes achieve maximum endurance at or above the tropopause. Turbopropeller aeroplanes reach maximum endurance at about 10,000 feet, and piston engine aeroplanes have their maximum endurance at sea level. You have learnt that there are two performance parameters in the cruise, range and endurance. Let us now consider range. Range is a more useful performance parameter than endurance, and one that aircraft designers continually try to improve. Whereas endurance is about airborne time, range is more concerned with distance covered, and it is, therefore, sometimes referred to as fuel mileage. Maximum range can be defined as being the maximum distance an aeroplane can fly for a given fuel quantity consumed, or to put it another way, the minimum fuel used by an aeroplane over a given distance. This latter expression of range is more commonly used for commercial operations. As a formula, range is simply the distance in nautical miles divided by fuel quantity in kilograms. However, in the same way as we did for the formula for endurance, we must adjust our range formula needs in order for it to give us useful information. The top line of the formula is air nautical miles per hour, and the bottom line of the formula is kilograms of fuel per hour. Thus, the formula now reads true airspeed divided by fuel flow. This is the formula for specific air range. The formula shows that specific air range is defined as the ratio of true airspeed over the fuel flow. You may recall from the endurance lesson that fuel flow is specific fuel consumption multiplied by drag for a jet, and specific fuel consumption multiplied by power required for a propeller-driven aeroplane. Looking at the formulae, it is now obvious that in order to maximize the specific range of the aeroplane, true airspeed must be high and the fuel flow must be low. Let us now focus on the specific air range of the jet aeroplane. We stated earlier that to maximize the range, the TAS must be high and the specific fuel consumption and the drag must be low. Shown on screen is the drag curve for a jet aeroplane. If the aeroplane were to fly at VMD, then of course the drag force would be at its lowest. Referring to the formula, it seems we have solved one of the points, namely how to make drag as low as possible. However, looking at the graph, notice that because the drag curve is fairly flat at the bottom, the speed may be increased significantly from VMD for only a small drag penalty. From the formula, we can therefore see that whilst drag has increased a little, which is bad for range, the airspeed has increased significantly, which is good for range. Consequently, the overall effect is that there is an increase in specific range. The speed at which the speed-drag ratio is maximized may be read from the graph at the tangent to the curve. You may recall that this speed was 1.32 VMD. Therefore, it is 1.32 VMD that is the speed for maximum range for a jet aeroplane. There is now only one remaining item left in the formula which still needs to be resolved. In order to increase range even more, specific fuel consumption must be decreased. You may recall that the only way to do this for a jet aeroplane is to operate at as high an altitude as possible. Operating as high as possible will give us a higher true airspeed for any given indicated airspeed, which again will improve the specific range. Having completed the analysis of range for a jet aeroplane, let us now examine specific air range for a propeller aeroplane. We stated earlier that to maximize the specific range, the TAS must be high and the specific fuel consumption and the power required must be low. Shown on screen is the power required curve for a propeller aeroplane. If the aeroplane were to fly at VMP, then of course its engine would be delivering minimum power required for level flight. Referring to the formula, it seems then that we have solved one of the components, namely to make power required as small as possible. However, at the graph, notice that because the power required curve is fairly flat at the bottom, the aeroplane speed may be increased significantly from VMP for only a small penalty increase in the power required. From the formula, we see that whilst power required has increased a little, which is bad for range, the airspeed has increased significantly, which is good for range. Consequently, the overall effect is an increase in the range. The point at which the speed-power ratio is at a maximum is the tangent point of the curve. You may recall that this speed is VMD. Therefore, it is VMD that is the speed for maximum range for a propeller aeroplane. There is now only one remaining item left in the formula which still needs to be resolved. In order to maximize range even more, specific fuel consumption must be decreased. However, you may remember that specific fuel consumption for piston aeroplanes is fixed, whereas for turbopropeller aeroplanes which use jet engines, the specific fuel consumption decreases with altitude. Having studied how to achieve maximum range for both jet and propeller engines, let us now examine what factors affect range. The first of the factors to discuss is the effect of weight. You will recall that increasing the weight of the aeroplane increases induced drag, and thus moves the total drag curve and power required curve up and right. Looking at the jet diagram, which uses drag, you can see for higher weights the aeroplane is subject to a higher drag force and therefore requires a higher rate of fuel flow. This will decrease specific range. However, notice that the speed for maximum range, 1.32 VMD, is now higher. For a propeller-driven aeroplane, it is much the same. At higher weights, more power is required. Therefore, fuel flow increases and range decreases. However, notice too that the speed for best range, VMD, is higher. Remember also that at higher weights, the operating altitudes are reduced, which for a jet aeroplane means that the specific fuel consumption increases, because at lower altitudes, the jet engine is less efficient. One of the most important issues that airline operators need to consider is the choice of the aeroplane they operate. This choice is mainly based upon the required aeroplane's payload and range. These requirements can be best described by going through a typical example. Shown on screen is the payload range graph for a Boeing 777. On the vertical axis is the payload in thousands of kilograms, and the horizontal axis shows the aeroplane range in thousands of nautical miles. On the right-hand side of the graph is a bar chart symbolizing aeroplane mass. Here, the aeroplane is at its dry operating mass, DOM, which essentially means the mass of the aeroplane without fuel or payload. This is shown on the bar chart and by the flashing blue marker on the bottom left-hand side of the graph. As the payload is added, notice that the blue mark moves up the payload axis. Notice too that the total mass of the aeroplane is increasing as shown by the bar chart. However, payload will reach a maximum when either there is no more space on the aeroplane or the aeroplane has reached its zero fuel mass, ZFM. Notice that the range at this point is 0 because no fuel has been added yet. This point is marked as A. Fuel is now added to the aeroplane and the marker point moves to the right, showing an increase in range. Adding fuel can continue until the maximum structural takeoff mass is achieved. This is shown by point B on the graph. Notice that the weight bar on the right is now at the top. Although maximum mass has been reached, it is unlikely that the tanks are full at this stage. To increase range further, more fuel must be added. But since the maximum mass has been achieved, the only way to add more fuel is if some of the payload is exchanged for fuel. Now the marker will start to move down and right. This shows that range is increasing, but the payload is decreasing. Swapping payload for fuel in this way can only continue until the tanks are full, as shown by point C. The only way to increase the range beyond this point, even though the tanks are full, is to remove the rest of the payload. At point D, the aeroplane has full tanks, maximum range, but no payload. In the majority of airlines, the trade-off between range and payload is carried out on initial aeroplane purchase and thereafter during in-flight planning. As a pilot, it is unlikely you will be required to work through these graphs other than to check and confirm the data that has been prepared in advance for you. Another factor affecting the range is the aeroplane's configuration. You will recall that deploying the flaps and undercarriage increases parasite drag and thus moves the total drag curve and power required curve up and left. Looking at the graph for the jet aeroplane and using the drag curve, you can see that with the gear and flaps deployed, the aeroplane has more drag and therefore needs more thrust, and which, in turn, requires greater fuel flow. This will decrease the range. However, notice that the speed for maximum range, 1.32 VMD, is now lower. Looking at the graph for a propeller aeroplane, you can see that matters are much the same. With gear and flaps deployed, more power is required. Therefore, fuel flow increases and range decreases. But also notice that the speed for best range, VMD, is lower. A point always to bear in mind in the cruise is that any increase in parasite drag will be detrimental to range and endurance. Increases in parasite drag can be caused by any number of things such as damaged and misaligned surfaces. The extra drag created by misaligned or misrigged airframe surfaces creates a type of drag called excrescence drag. This can be more than 4% of the airplane's total drag. Careful pre-flight inspection should reveal misaligned or misrigged surfaces. An important point to consider over which the pilot has direct control is aeroplane trim. A pilot must periodically check the aileron and rudder trim, the spoiler misfare, and the trailing edges to ensure that the aeroplane is in trim and is in balanced flight. Monitoring the aeroplane's control surfaces will help to reduce the extra drag and extra fuel consumption that out of trim and unbalanced flight can cause. Lastly, contamination on the airframe from airframe icing can affect fuel flow. This icing will not only change the shape of the wing, making it less efficient at producing lift, but it will also increase weight and drag. All this is detrimental to aircraft performance and will reduce the aeroplane's range. Wind is the next of the major factors affecting the range of an aeroplane. Headwinds will cause the aircraft to travel slower over the ground and therefore cover less distance for a given level of fuel consumption. Thus, in headwinds, range is reduced. In order to minimize this effect, the speed of the airplane is increased by a margin slightly less than the amount of the headwind. The increase in speed will increase the thrust and the power required, and therefore the fuel consumption. But on a positive side, the aeroplane will be exposed to the headwind for a shorter time period if it is flying faster. This higher speed then recovers some of the range lost caused by the headwind. On the contrary, a tailwind will increase the ground speed and increase the distance covered for a given level of fuel consumption, thereby increasing range. For maximum range with a tailwind, the speed for the best range should be decreased slightly so as to reduce the thrust and power required. This will therefore reduce the fuel flow and increase the range a little more. The reduction in speed is slightly less than the speed of the tailwind component being experienced. The headwind and tailwind speed changes can be seen on the drag and power curves for the jet and propeller aeroplane. However, to simplify the graphics, we'll just concentrate on the drag curve for the jet aeroplane. With a 20 knot headwind, the origin of the tangent line moves 20 knots to the right. Notice that the tangent meets the curve at a point corresponding to a higher speed, thus confirming that in a headwind, the speed for best range is higher. The opposite is the case in a tailwind scenario. With a tailwind of 20 knots, the origin of the tangent line moves 20 knots left. Notice that the tangent meets the curve at a point corresponding to a lower speed. This confirms that in a tailwind, the speed for best range is lower than in conditions of zero wind. The effect of altitude on the range of an aeroplane is important, especially for a jet aeroplane. On screen is the formula for the specific air range for a jet aeroplane. Let us examine how the variables change with increasing altitude. As aeroplane operating altitude increases, the colder air and requirement for increasing RPM cause the specific fuel consumption to decrease, which will help to increase the specific air range. However, there are two other variables left to consider, namely the true airspeed and the drag. If you think back to the part of the lesson where we were analysing the effects of altitude on the various speeds, you will recall that if the aeroplane operates at higher and higher altitudes at the constant indicated or calibrated airspeed of 1.32 VMD, the true airspeed increases. The effect of increasing altitude and therefore increasing true airspeed acts together with the reducing specific fuel consumption to help increase the specific range. However, you will recall that with altitude, as the true airspeed increases and the local speed of sound decreases, the Mach number increases. This means the aeroplane is approaching the speed of sound and approaching the maximum operating Mach number, MMO. The problem with this is that beyond a certain Mach number, the compressibility factor and approaching shock wave will cause drag to increase. This will be detrimental to the specific range. On the graph, you can see that the range stops increasing with altitude because of this effect. Consequently, there will be an altitude beyond which the range starts to decrease. This is because the Mach number will be too high, and the penalty due to drag will outweigh the benefits of increasing TAS and reducing specific fuel consumption. Consequently, the specific air range will start to reduce. You will notice on the graph that there is an altitude at which the specific range is greatest. In our example, this is 33,000 feet. This altitude is called the optimum altitude. It is defined as being the pressure altitude which provides the greatest specific range, or fuel mileage, at a given weight and speed. Flying higher or lower than the optimum altitude will decrease the range of the aeroplane. It is important to understand that the optimum altitude is not fixed. You will recall that as the weight decreases through fuel burn, the drag curve moves down and left. Therefore, the best range speed, 1.32 VMD, falls and the total drag decreases. Therefore, with decreasing weight, the aeroplane needs to slow down to maintain the best range speed. As it does so, the Mach number will of course also decrease, meaning that the aeroplane is not limited by the high Mach number and corresponding high drag. This fact allows the aeroplane to climb a little. As the aeroplane climbs, the Mach number will increase again to its previous limiting value, and drag will increase back to its previous value. But more importantly, the higher altitude has increased the true airspeed and decreased the specific fuel consumption. Therefore, the specific air range increases. This means that over time, as the weight decreases with fuel burn, the optimum altitude increases. Plotting the optimum altitude over time gives us the graph shown on screen. In order for the aeroplane to maximize the specific range, the aeroplane must stay with the optimum altitude as the optimum altitude slowly increases. Climbing in this way is sometimes called a cruise climb. But carrying out a cruise climb is not always possible, since air traffic control restrictions and airspace congestion may predetermine flight cruising levels. If this is the case, in order to stay close to the optimum altitude, step climbs may be performed. Step climbs essentially mean that the aeroplane climbs to about 2,000 feet above the optimum altitude and levels off. As fuel is used and weight falls, the optimum altitude will increase to a point where it is again 2,000 feet above the aeroplane's current level, but it can take up to 3 hours for it to do so. At its current level, the aeroplane can then climb 4,000 feet and level off, so that it will once again be 2,000 feet above the optimum altitude. But, if the last step climb is within 200 nautical miles of the top of descent, then the fuel saving is negated and the aeroplane should remain level. The step climb process can be repeated throughout the cruise, and it helps to explain why the cruise altitudes at the end of the flight are higher than at the start. Carrying out step climbs in this way, rather than always staying with the optimum altitude, will increase fuel consumption by about 1% and therefore decrease the maximum range by 1%. This may not sound like much, but over a year, a typical 747 would have used an extra 34,000 tons of fuel. If an aeroplane did not even step climb and simply remained at a constant altitude during the cruise, then the aeroplane would increase its fuel consumption by 10% compared to flying constantly at the optimum altitude. This demonstrates just how important altitude and speed control are in the cruise for a typical commercial flight. Having discussed the effect of altitude on the jet aeroplane, let us now consider the effect of altitude on the propeller aeroplane. In general, though, we may say that most turbopropeller aeroplanes operate significantly lower than their jet counterparts. Turbopropeller aeroplanes seldom operate above 30,000 feet, and therefore never really suffer from the effects of getting close to the speed of sound. Turbopropellers are based on the same engine design as a pure jet. Therefore, the effect of altitude on the turbopropeller is very similar to the jet aeroplane. As altitude increases, the increasing TAS and slightly decreasing specific fuel consumption help to improve the specific range. However, this benefit is offset a little by the increasing power required at higher altitude. So, while specific range does improve with altitude, above 10,000 feet it only improves by a small amount. The choice of altitude may depend more on the wind considerations and the time and fuel considerations involved in climbing to the selected altitude. The other type of propeller aeroplane is that driven by a piston engine. You will recall that the piston engine aeroplane has a more or less fixed specific fuel consumption, even though specific fuel consumption is lowest at high manifold pressures, low RPM, and with the mixture correctly set. Therefore, the only remaining variables in the specific air range formula for the piston engine aeroplane are the true airspeed and the power required. As the aeroplane operates at higher and higher altitudes, the power required to maintain the range speed will increase. This, of course, is detrimental to range. However, as altitude increases, true airspeed increases for any given indicated airspeed. This fact offsets the increase of power required, and therefore the specific range slowly increases with altitude. However, the aeroplane will reach an altitude where the throttle needs to be fully advanced to keep the selected speed. This altitude is called the full throttle height. Beyond this altitude, the selected power and selected airspeed cannot be maintained, and the aeroplane will slow down. Very soon after this altitude, the true airspeed will also start to fall despite the decreasing density. This fact, combined with the constantly increasing amount of power required, means that the specific range will decrease. As a result, maximum specific range will be attained just after full throttle height. The effect of headwinds and tailwinds on the range of the aeroplane can play a significant role in the choice of cruising altitude. For example, if there is a considerable headwind at the selected cruising altitude, this will be detrimental to the range. In this case, it may be beneficial to operate at a different altitude where the winds might be more favourable. In large commercial operations, most of these considerations are dealt with prior to the flight by the flight planning personnel. However, in smaller operations, and if conditions change in flight, a pilot may have to carry out a wind-altitude trade-off calculation. Information enabling the pilot to do this is usually given in the aeroplane flight manual, an example of which is shown on screen. The graph shown on screen shows the relationship between the speed of the aeroplane and its range. Shown here is the speed for best range, which for a jet aeroplane is 1.32 VMD. In commercial operations, this speed is more commonly referred to as the maximum range cruise, or MRC. However, maximum range cruise speed is seldom flown. Usually, a higher speed is used. Looking at the top of the graph, you will notice the line is fairly flat. This means that a significant speed increase can be achieved with only a small compromise in range. This higher speed is called the long-range cruise. The long-range cruise speed is about 4% higher than the maximum range cruise speed, and as such, the specific range reduces by about 1%. The reason for using this higher speed is simply that there are costs other than fuel which need to be considered in commercial operations. A more detailed explanation of the relationships of these costs and how they affect the operations will be dealt with later on. This last section on the general performance principles in the cruise deals with summarizing the performance speeds using the drag and power required curves. Firstly, we will go through the performance speeds on the drag curve. You may recall that there were three reference speeds. These were VMP, VMD, and 1.32 VMD. Since this is the drag curve, the speed on the bottom of the curve is called VMD. The other two speeds are VMP and 1.32 VMD. VMP is about 0.76 lower than VMD. 1.32 VMD is higher than VMD and is found on the tangent of the drag curve. These three reference speeds mean different things for different aeroplanes, and knowing which reference speed is to be used for a specific performance task is important. For example, you may recall that the best endurance speed for a jet aeroplane is VMD, but the best range speed is 1.32 VMD. Best endurance speed for a propeller is VMP, but the best range speed is VMD. There are other speeds though. During the climb lesson we learnt that the best angle of climb speed, Vx, is for a jet aeroplane VMD, but for a propeller aeroplane it is VMP. The best rate of climb speed, Vy, is for a jet 1.32 VMD, but for a propeller aeroplane it is VMD. Lastly, during the descent lesson you learnt that the speed for the minimum angle of descent, or best glide speed, is VMD, and the speed for the minimum rate of descent is VMP. It's obvious that so many speeds may cause confusion to students. Placing the speeds together in this way helps you to see where they are in relation to the three reference speeds and in relation to one another. What is equally important though is for you to have a tool which you can manipulate to give the desired results. This is what the graph aims to provide. You may remember that as weight increases, the drag curve moves up and to the right. This means that not only drag is increased, but also all the performance speeds are higher. The reverse is true as weight is decreased. The drag curve moves down and left, showing that drag decreases and the performance speeds are lower. As gear and flap are deployed, the drag curve moves up and left, showing drag increases, but the performance speeds are lower. Retracting the undercarriage produces the opposite effect. Drag decreases, but the performance speeds are higher. Using the graph in this way, we can simplify a lot of the material that you need to learn. Just as in the previous section where the performance speeds were shown on the drag curve, we can do the same with the power required curve. Firstly, the three reference speeds need to be identified on the graph. Since this is a power required curve, the speed at the bottom of the curve is the velocity of minimum power, VMP, as shown. The next speed is VMD. This is slightly higher than the VMP and is found at the tangent point on the power required curve. The last speed is 1.32 VMD and is shown here. It is now possible to place the performance speeds we described in the previous section beneath the relevant reference speeds. Doing this completes the placement of all the speeds on the power curve for both jet and propeller aeroplanes. As before, the power curve can be manipulated to show the effect of certain conditions, giving you a tool to solve basic problems. Increasing weight will move the curve up and right, therefore showing the increase in power required, but it also shows that the performance speeds are higher. If weight decreases, then the reverse is true. Similarly, with the deployment of flaps and undercarriage, the curve will move up and left, showing that the power required increases, but the performance speeds reduce. Again, the reverse is true when the gear and flaps are retracted. Hopefully from this demonstration, you can see the importance of using a graph for the reference speeds. The principles you have learnt form a large part of the requirements of the ATPL examination, but more importantly, these principles will allow you to make accurate and informed decisions in routine flight management, and especially in emergency situations where your training becomes a vital safety cushion. This completes the lesson on the general performance principles in the cruise.
The landing stage of flight is defined as being that stage of flight commencing from 50 feet above the landing threshold and terminating when the aeroplane comes to a complete stop. The 50 feet point is sometimes referred to as the landing screen height. The landing screen height is fixed at 50 feet for all classes of aeroplane, unlike the takeoff screen height, which is 35 feet for Class A aeroplanes and 50 feet for Class B aeroplanes. At the landing screen height, the aeroplane must have attained the landing reference speed known as VREF. VREF for Class A aeroplanes must be no less than the greater of 1.23 times the stall reference speed in the landing configuration, and the velocity of minimum control in the landing configuration. VREF for all other classes of aeroplane must be no less than 1.3 times the stall speed in the landing configuration. VREF is a very important speed to attain, since the landing distances in the aeroplane flight manual are based on aeroplanes flying at VREF. Therefore, if a landing aeroplane is not at VREF, the landing distance given by the manual will not be achieved by the pilot. A landing carried out at a speed other than VREF could seriously jeopardize the safety of the landing. The landing can be divided into two parts. We call these the airborne section and the ground run or landing roll. The first part, the airborne section, starts from the landing screen height of 50 feet and ends when the aeroplane's main wheels touch the landing surface. The airborne section is usually given as being about 1,000 feet in length. Within the airborne section, certain critical actions take place. On descending through the screen height, the thrust is reduced to 0, and the aeroplane pitch attitude is increased slightly so that the aeroplane is in a slight nose-up attitude. The increase in pitch attitude helps to arrest the rate of descent, and the reduction in thrust to 0 reduces the speed. This procedure of reducing thrust and increasing pitch is known as the landing flare, although other terms like a round-out are commonly used. The landing flare will allow the aeroplane to touch down onto the runway using the main wheels first. It is important to understand that the technique of flaring the aeroplane differs from one aeroplane to another, and especially so between light general aviation aeroplanes and large commercial jet airliners. The second part of the landing is the ground run or landing roll. This is the distance covered from touchdown until the aeroplane comes to a full stop. As with the airborne section, there are a few critical actions that are carried out. Once the main wheels have settled onto the landing surface, reverse thrust and lift spoilers can be activated, and as the speed decreases further, the nose wheel will then settle onto the landing surface. Braking force is now applied, and the aeroplane will slow to a stop. However, in normal operations, the aeroplane does not stop on the runway. Rather, the aeroplane is slowed to a safe speed where it can then be steered off the runway and taxied to the disembarkation point or ramp. The combined length of the airborne section and the ground run or landing roll is known as the landing distance required. Pilots need to make sure that the landing distance required does not exceed the available landing distance. In order to better understand landing performance, we need to analyse the forces acting upon the aeroplane, and how these forces might be modified throughout the landing. The first of the forces that we will consider is weight. As you have learnt already, weight acts vertically downwards towards the centre of the Earth from the centre of gravity. During flight, weight is mainly balanced by lift. However, once the aeroplane is on the ground, weight is balanced by the reaction of the ground acting up through the wheels on the undercarriage. The weight of the aeroplane on landing will be less than at takeoff due to the fact that fuel has been consumed. There is, however, a maximum structural landing mass which must not be exceeded. Let's now consider lift. Whilst lift helps to balance weight when in the air, once the aeroplane is on the ground, lift is no longer required. In fact, during the landing roll, lift is detrimental to the landing performance. Producing lift will reduce the load placed on wheels and therefore decrease the braking effect. In large commercial aeroplanes, once the main wheels have settled on the runway, the lift spoilers or lift dumpers are deployed, which act very quickly to disrupt the airflow over the wing and destroy lift. Whilst in level flight, the forward-acting force of thrust is essential to maintain sufficient speed for the wings to provide lift. During landing, because the aim is to bring the aeroplane to a stop, the thrust force must be reduced to zero. Any residual thrust would be detrimental to the landing performance. However, large propeller and jet aeroplane engines have the capability of redirecting the force of thrust in order to generate a braking effect on the aeroplane. This is known as reverse thrust. Reverse thrust helps to reduce the aeroplane's forward speed. Reverse thrust capability is especially important in conditions where braking force is reduced due to ice or water contamination on the runway. Jet engines produce reverse thrust by using one of several methods, but all jet engines follow the same basic principle, which is to redirect the jet efflux in a forwards direction. This animation shows an example of a jet engine in reverse thrust mode. Many modern aeroplanes have a safety device whereby reverse thrust is not activated until a certain value of the aeroplane's weight is pressing down on the main wheels, and until the wheels have reached a certain speed of rotation. Once the aeroplane's reverse thrust system has detected this, reverse thrust is activated, and the engine will reconfigure itself so that the exhaust gas flow can be redirected forwards. However, pilots need to recognize that the process of getting the engines reconfigured to generate full reverse thrust takes time, and so the aeroplane will have travelled a small distance from the touchdown point before reverse thrust takes effect. This fact reduces the effective time period during which reverse thrust can be used. Therefore, the effectiveness of reverse thrust on landing is reduced. It is important to note too that jet engine reverse thrust cannot be maintained right up to the point when the aeroplane comes to a full stop. Reverse thrust must be deactivated before the forward speed reduces to a minimum value. As the aeroplane slows down, the redirected airflow may start to be re-ingested into the compressor, as shown on screen. This means that the jet engine recycles its own gas flow, which significantly increases the engine temperatures. But it also means that debris on the runway can be sucked into the engine, potentially causing major damage. As a result of this danger to the engines at low forward speeds, reverse thrust must be deactivated below about 50 knots. The combined effect of late reverse thrust activation and early reverse thrust deactivation means that the time period for which reverse thrust can be used may be quite short. Large turbopropeller aeroplanes are also able to generate reverse thrust by redirecting the airflow forwards, but they do so in a very different way than that employed by a jet engine. For forward flight, the propeller blade is angled in such a way as to displace air backwards, thus producing forward thrust. This produces a forward force, as shown. In order for the propeller blade to direct air forwards and create a rearward acting force, the blade angle must change to the position illustrated here. The blade angle required for the propeller to generate reverse thrust is known as reverse pitch. Because only a change of blade angle is required, a propeller aeroplane can switch from forward to reverse thrust far quicker than a jet aeroplane. This means that a propeller aeroplane can use reverse thrust earlier in the landing roll than a jet aeroplane. A propeller aeroplane can also maintain reverse thrust until the aeroplane comes to a full stop. This capability gives the propeller aeroplane a greater braking advantage over the jet aeroplane during landing. In summary, the usable period of reverse thrust in the landing roll is shorter for a jet aeroplane than for a propeller aeroplane. For this reason, the authorities have laid down less stringent landing performance regulations for propeller aeroplanes. The precise nature of these regulations will be discussed later. However, it is important to note here that when calculating the landing distance to comply with the landing regulations, the use of reverse thrust is not considered except when the runway is wet. Therefore, when reverse thrust is used, the landing distance achieved should be considerably less than the calculated landing distance. Let us now consider the action of the drag force during landing. You may recall that there are several forms of drag. The main types of drag are parasite drag and induced drag. However, whilst the aeroplane is on the ground, during takeoff and landing, wheel drag must be considered alongside the aerodynamic drag just mentioned. The aim of the landing is to bring the aeroplane to a stop safely within the confines of the runway. In order to decelerate, sufficient rearward directed forces need to act on the aeroplane. Consequently, in addition to reverse thrust, aerodynamic drag plays a very crucial role in landing. Of the two types of aerodynamic drag, we'll deal with induced drag first. Induced drag is dependent on lift and is proportional to angle of attack. During the airborne section of the landing, there is still a large amount of lift being generated, and the angle of attack is relatively high. This means that induced drag is far higher than in cruising flight. However, when the aeroplane nose wheel touches the runway, the angle of attack is almost nil. Induced drag is consequently reduced to almost zero. The second form of aerodynamic drag is parasite drag. Parasite drag is a function of the aeroplane's forward-facing cross-sectional area, more accurately known as form drag, and of the aeroplane's forward speed. The configuration of the aeroplane for landing is such that the flaps and slats are fully extended, which significantly increases the aeroplane's form drag, and therefore significantly increases parasite drag. Once the aeroplane touches down and the spoilers and speed brakes are deployed, parasite drag increases even further. However, as the speed rapidly decays after touchdown, so will the parasite drag, eventually decreasing to zero once the aeroplane reaches a full stop. In summary then, the aerodynamic drag comprising induced drag and parasite drag will be very high during the early part of the landing, but very soon after touchdown will decay rapidly. Having discussed aerodynamic drag, let's now consider wheel drag and brake drag. Wheel drag is the friction force between the wheel and the runway and with the wheel bearings, whereas brake drag is the friction force between the brake discs and the brake pads. Wheel drag will come into play as soon as the aeroplane touches down on the runway. However, as friction is a function of the force pushing two forces together, because there is still a lot of lift being generated, wheel load is small during the initial part of the landing run, and therefore wheel drag is also small. As speed reduces and as lift is destroyed by the spoilers, the wheel load increases, which in turn increases the wheel drag. Therefore, wheel drag increases throughout the landing roll and will reach a maximum value just before the aeroplane comes to rest. This image shows that brake drag is by far the most important and the most effective of the various drag forces during the landing, since it provides the greatest retarding force. However, brake drag is only effective if there is also sufficient wheel drag or wheel friction between the tyres and the runway. If wheel drag is low, brake drag will also be low. Consequently, the brakes are effective only if there is sufficient friction between the tyres and the runway. Using this example, we see that during the early part of the landing run, when there is not much load on the wheels and therefore not much wheel friction, brake drag is consequently ineffective in slowing down the aeroplane. However, as the lift reduces and more weight is placed on the wheels, brake drag does become more effective in slowing down the aeroplane. Therefore, brake drag increases as the landing roll progresses. This concept is why pilots need to destroy lift as soon as possible after touchdown, so that the braking action can be at its peak effectiveness early on in the landing. This diagram shows how important the spoilers are in improving the brake drag effect. In most large commercial aeroplanes, however, the braking action may not actually be carried out by the pilots. Instead, it can be carried out by a highly effective automatic anti-skid braking system. This braking system can be set to low, medium or high braking levels, or levels 1 through to 3, and is especially important to use when landing on contaminated runways. These pictures show what happens when the anti-skid system fails and the wheels remain locked. This last part on the discussion of the forces will summarise the drag forces on the aeroplane during the landing roll. The first of the drag forces we discussed was aerodynamic drag. As speed decreases during the landing run, aerodynamic drag comprising of parasite and induced drag decreased. Brake drag, on the other hand, increased during the landing roll as more load was placed on the wheels. Notice that during the early part of the landing roll, aerodynamic drag provides the majority of the drag, whereas once the speed has dropped below 70% of the landing speed, brake drag provides the majority of the drag. The last line on the graph is total drag. From this line, you can see that during the landing roll, total drag increases. Overall, you can see how important brake drag is. If the brakes were to fail, or the landing surface is very slippery, then the loss of braking would cause the landing performance to massively deteriorate, therefore increasing the landing distance. Next, we'll examine what determines the landing distance, and also what roles the four forces play. In order to do this, let's briefly detail the formula that is used to calculate the landing distance. The letter S is the displacement or distance required to stop from a specified speed, which is v. With a given deceleration d, deceleration is force divided by mass. The force is aerodynamic drag plus the braking coefficient, which is a function of wheel load minus thrust, or in the case of reverse thrust, plus thrust. Expanding the formula in this manner allows you to see how a change in one of the variables has a knock-on effect on the landing distance. We'll now analyse in detail all the factors that can affect the takeoff, with our principal concern being how these factors affect the landing distance. The first of the factors that affect the landing is the effect of mass. Increasing mass has three significant effects on the landing, all of which can be observed in the formula for the landing distance. The first is that a greater amount of mass for a given force applied will reduce the deceleration that the aeroplane can achieve. Essentially, the heavier the object, the harder it is to decelerate it. This is the effect of momentum. More mass will create more momentum. If the deceleration of the aeroplane is reduced, then the landing distance will increase. The second effect is not as apparent as the others. A heavier aircraft requires more lift in order to fly. To get this extra lift, the aeroplane will need to travel faster through the air. This means that the aeroplane will need to decelerate from a higher landing speed. Stopping from this higher speed will require a greater distance, and therefore the landing distance will increase. A third effect of mass is that there will be more load on the wheels, and therefore wheel drag will increase. An increase in wheel drag will allow a greater braking force to be applied. This increases the deceleration of the aeroplane. If the deceleration of the aeroplane is increased, then the landing distance will decrease. In summary, the effect of increasing mass has 3 effects on the landing performance. 2 of them are detrimental, but 1 is beneficial. The overall effect, as shown on screen, is that increasing the landing mass increases the landing distance. Always ensure that the aeroplane mass is within the performance limitations and never exceed the maximum structural landing mass. Mass calculations are dealt with more comprehensively in the Mass and Balance course as part of the theoretical training. The next factor which will affect the landing performance is the air density. This has 2 effects. The first effect is that a reduced density means that the amount of reverse thrust produced by the engine is reduced. Reduced engine reverse thrust will decrease the deceleration force, and as a result the landing distance will be increased. The second effect of a low density concerns the landing speed. You will recall that although the landing speed is based upon an indicated airspeed, the true airspeed will be higher in low density. This means that the aeroplane is actually approaching at a faster speed and will therefore require a greater landing distance to stop in. Although the full explanation is outside the scope of this course, high temperatures, high altitudes and high humidity will all decrease the density of air and therefore increase the landing distance. A useful statement to memorize is that high, hot or humid conditions all decrease air density and aeroplane performance. The next factor that will affect the landing performance is the wind. Shown here is a landing with no wind in order to create a comparison example. You will recall that headwinds decrease the true ground speed of the aeroplane for any given indicated airspeed. Thus, during a headwind, the forward speed over the landing surface is much less, and as a result, the distance required to bring the aeroplane to rest is decreased. A tailwind will have the opposite effect, and it will increase the ground speed for a given indicated airspeed. Thus, during a tailwind, the forward speed over the landing surface is much greater, and as a result, the distance required to bring the aeroplane to rest is increased. When examining the effects that winds have on landing performance, it is recommended that you do not use the actual wind that is given, just in case the wind changes to a worse condition than the one you have planned for. When calculating actual landing distances, it is recommended that you assume only 50% of the headwind component and 150% of the tailwind component. Most performance graphs that calculate the landing distance have the 50% headwind and 150% tailwind recommendation already applied. The example shown here demonstrates this. An important note is that there is no allowance for crosswinds, and therefore no safety factor for crosswinds. Crosswinds present an additional complication because of the effect of potentially crossed controls, which would have to be applied because the wind will tend to push the aeroplane off the centre line. These issues mean that aeroplanes are given maximum crosswind limits. The next factor that can affect the landing performance is the slope of the runway. Slope has an impact on the landing distance because of its effect on how the component of weight acts along the longitudinal axis of the aeroplane. When the aircraft is on an upslope, the weight still acts towards the centre of the Earth, but there is a component of weight, shown here, which acts in the direction of drag, that is, backwards along the longitudinal axis. This will increase the deceleration of the aeroplane and therefore decrease the landing distance. Conversely, when the aeroplane is on a downslope, the weight component now acts in the direction of thrust. This adds to the forward force, therefore it will decrease the deceleration and increase the landing distance. A rough calculation to help quickly quantify the effect of slope is to assume that for every 1% slope, the landing distance is affected by 5%, or a factor of 1.05. The slope at some airfields means that the landing may only be possible in one direction. These are called unidirectional runways. Treat these runways with extra caution and always check that the current wind velocity will still allow a safe landing, since you may be forced to land with a tailwind. Although it will be made clear later, the landing regulations state that upslopes are not to be considered when calculating the landing distance, since upslopes will help to reduce the landing distance. Most landing performance graphs assume a paved hard surface. If the condition of the runway is not like this, then the effect on the landing distance needs to be understood and corrections applied. A lot of small airfields have grass runways. The grass will increase the drag on the wheels. However, grass severely reduces the wheel friction to the runway compared to a paved runway, and therefore the wheel cannot be retarded efficiently by the brakes. Otherwise, the wheel will lock and the wheel friction with the runway will reduce even further. The overall effect is that grass runways will increase the landing distance. In light general aviation aeroplanes, this increase in landing distance is about 15% compared to a landing on a paved surface. However, most landings that you will carry out throughout your professional career will undoubtedly be on hard paved runways. If the runway is covered partially or fully by contaminants such as standing water, snow, slush or ice, then pay special attention to effects that they will have on the landing distance. These substances will have two main effects. The first effect is that they will create impingement drag. But more importantly, the second effect is that these substances will substantially reduce the friction between the wheel and the runway. Therefore, the wheel cannot be retarded efficiently by the brakes. The graph clearly shows that as a result of the reduced friction and therefore the subsequent reduced braking action, any contamination of the runway due to water, snow, slush or ice will significantly increase the landing distance. This table shows the deceleration of an aeroplane during the landing based on different surfaces. You can see the large reduction in deceleration on icy runways. Typically, on a dry runway, the braking coefficient of friction is between 0.8 to 1. But on wet, slippery or icy runways, the braking coefficient of friction can fall to less than 0.2. Shown to the left and right of the runway friction values are the runway terminology and ATC friction reports. These help to provide aircrew with more information about the conditions for landing. Because of the lack of effective braking on slippery surfaces, the aerodynamic drag and reverse thrust become much more important in bringing the aeroplane to a stop, as shown in the diagram to the right. Notice that on flooded or icy runways, reverse thrust accounts for 80% of the deceleration force, confirming its importance as a deceleration tool. Next, you'll hear a commentary from a Canadian air traffic controller about a situation when the runway was slippery.
We had some freezing drizzle fall while the temperature remained near freezing. This left an ice-covered runway. The Dash 8s didn't say anything about braking action. Then a BAE 146 landed. I watched him drop off the radar and gave him several seconds to get slowed down. I told him to take the first available right turn and report off the runway on my frequency, so the Boeing 757 behind him could get a landing clearance. He responded saying,
"Well, we're still sliding here. We'll let you know when we get stopped."
After what seemed like an eternity, a shaken voice came over the radio.
"We're just getting it stopped now, about 75 feet from the end of the runway. We'll call the braking action nil."
I reported this to the 757, anticipating that he may not want to land. He asked for a landing clearance, which I gave him. Upon landing, the 757 reported braking action fair and turned onto a taxiway about 1,500 feet from the end of the runway, without a hint of panic in the voice. What a difference thrust reversers can make.
This part of the lesson is interactive, and it will help you to understand the relationship between the various types of contaminations, the braking effect with these contaminations, and the effect on the stopping distance. The aeroplane is travelling from left to right. You can select the type of surface you want to use, either dry, wet or icy. Once you have done so, looking to the left hand of the screen, move the slider on the horizontal bar underneath the 3 gauges. Moving the slider to the right increases the applied brake force. Be careful though, too much braking force will cause the wheels to lock, and this will change depending on the runway contamination. When you have completed this section, click on the forward arrow to continue with the lesson. An important point to note is that there is a distinction between the definitions of a damp, wet or contaminated runway. A runway is considered to be damp when there is moisture present on the surface which changes its colour, but insufficient moisture to produce a reflective surface. A wet runway is one whose moisture level makes the runway appear reflective, but there are no areas of standing water in excess of 3 mm deep. Wet runways can cause the average dry landing distance to increase by as much as 50%. A contaminated runway is one where more than 25% of the runway is covered in a layer of moisture whose specific gravity is equivalent to a depth of 3 mm or more of water. The importance of runway contamination cannot be stressed enough, as many fatal accidents may have been avoided had due account been taken of the situation. From what you have learnt so far, it is vital that the pilot be aware of the type of runway contamination, its depth, its extent, its effect on the braking, and of course its overall effect on the operation concerned, in this case the landing. The information on the runway contamination and braking effect can be given to the pilot through a report. These reports are either by SNOTAM, Runway State Code, PIREPS, or spoken by Air Traffic Control. These reports may include braking action or braking coefficient. Use any runway report together with your aeroplane flight manual and standard operating procedure to best gauge the landing technique and landing performance. The second type of hydroplaning is called viscous hydroplaning. It occurs because of the viscous properties of water acting like a lubricant. A thin film of fluid not more than 1/1000th of an inch deep cannot be penetrated by the tyre in the footprint area, and the tyre rolls on top of the film. Viscous hydroplaning can occur at a much lower speed than dynamic hydroplaning, but it requires a smooth surface. The most positive method of preventing this type of hydroplaning is to provide a microtexture to the pavement surface which breaks up the film of water, allowing it to collect into very small pockets. This means that the tyre footprint will sit on the peaks of the textured surface as shown, and not the film of water. Reverted rubber hydroplaning is a complex phenomenon which over the years has been the subject of a variety of explanations. Reverted rubber hydroplaning requires a prolonged, locked wheel skid, reverted rubber, and a wet runway surface. The locked wheels create enough heat to vaporize the underlying water film, forming a cushion of steam that lifts the tyre off the runway and eliminates tyre-to-surface contact. The steam heat reverts the rubber to a black gummy deposit on the runway. Once started, reverted rubber skidding will persist down to very low speeds, virtually until the aircraft comes to rest. During the skid, there is no steering capability and the braking effect is almost nil. Reverted rubber hydroplaning is greatly reduced in modern aeroplanes due to the standardization of advanced anti-skid braking systems, which prevent wheel lock-up. This section will provide advice and guidance on how to land on contaminated runways. Firstly, check the current weather and the runway conditions using the most accurate information possible. Once this has been done, completely reassess the landing performance data to ensure satisfactory compliance to the regulations. Ensure you're at VREF at the landing screen height and prepare to land the aircraft in the touchdown zone within the 1,000 feet target of the airborne segment. Land on the centre line with minimal lateral drift and without excess speed. Arm auto spoilers and auto brakes as appropriate, which assure prompt stopping effort after touchdown. For aeroplanes fitted with automatic anti-skid brakes, the brakes will be applied above the dynamic hydroplaning speed, but for aeroplanes without this system, only apply the brakes below the dynamic hydroplaning speed. The flare should lead to a firm touchdown, sometimes described as flying the aeroplane onto the runway. Positive landings will help place load on the wheels, which will increase braking effectiveness and squeeze out the water from the tyre footprint area. Do not allow the aeroplane to float, and do not attempt to achieve a perfectly smooth touchdown. An extended flare will extend the touchdown point. Soft touchdowns will delay wheel spin-up and delay oleo compression, which is needed for auto brake and auto spoiler activation. After main gear touchdown, do not hold the nose wheel off the runway. Smoothly fly the nose wheel onto the runway by relaxing aft control column pressure. Raise spoilers as soon as possible after touchdown or confirm auto spoiler deployment. If the aeroplane does not have auto brakes, then initiate braking once spoilers have been raised and nose wheel has contacted the runway. Apply brakes smoothly and symmetrically. Initiate reverse thrust as soon as possible after touchdown of the main wheels and target the rollout to stop well short of the end of the runway. Leave a margin for unexpectedly low friction due to wet rubber deposits or hydroplaning. Of all the phases of flight, it is the landing phase which is the most susceptible to severe weather conditions. The low altitude, low speed, low thrust settings and high drag during the landing phase mean that the aeroplane is at its most vulnerable. The video sequence here shows how dangerous wind shear can be in destabilizing the aeroplane during an approach to land. Landing when wind shear is observed or forecast should be avoided, but if conditions are within limits, then landing at a higher speed should be used. But caution should be exercised since the higher landing speed will greatly increase the distance of the airborne section and ground roll of the landing. The microburst is the single most hazardous weather phenomenon to aeroplanes close to the ground. We briefly discussed the microburst phenomenon in the takeoff section, but in landing it represents an even greater threat. However, there are certain clues which can give a pilot advance warning. The most obvious clue to a potential microburst are the tendrils of rain found beneath a storm cloud, which are called virga or fall streaks. Virga is precipitation falling but evaporating before it reaches the ground, as shown here. In the absence of specific guidance, here are some suggested techniques for identifying and dealing with a microburst encounter whilst on the approach to land. Initially, there will be an increase in airspeed and a rise above the approach path caused by the increasing headwind. On modern aeroplanes, a wind shear alert is usually given. This should be seen as the precursor to the microburst. Any hope of stabilized approach should be abandoned and a missed approach should be initiated.
Wind shear, wind shear, wind shear.
Without hesitation, the power should be increased to go around power, the nose raised, and the aeroplane flown in accordance with the missed approach procedure. Typically, the nose attitude will be about 15 degrees and the control column should be held against the buffet or stick shaker. The initial bonus of increased airspeed may now be rapidly eroded as the downdraft is encountered. Airspeed will fall and the aeroplane may start to descend despite high power and high pitch angle. The point at which the tailwind starts to be encountered may be the most critical. The rate of descent may lessen, but the airspeed may continue to fall, and any height loss may now break into obstacle clearance margins. Maximum thrust is now usually needed, and the nose attitude kept high on the stall warning margins to escape the effects of the tailwind. Had the go-around not been initiated at the early warning stage, then it is highly unlikely that the aeroplane will survive the encounter. Because wind shear, heavy rain, poor visibility, runway contamination and microbursts are hazards very closely associated with thunderstorms, it is advisable never to land with a thunderstorm at or in the immediate vicinity of the aerodrome. Delay the landing or consider diverting. There are too many cases to list of pilots who have attempted to land in bad weather and they have sadly perished along with many passengers. Most of these occurrences were avoidable had due account been made of the situation. The last factor to consider that affects the landing is the configuration of the aeroplane in terms of the flap settings. Flaps are trailing edge devices used to increase the camber of the wing and generate more lift, thereby reducing the landing speed. However, the use of a lot of flap will dramatically increase aerodynamic drag as well. This is a benefit in landing and helps to slow the aeroplane down. Let's take a look at how different flap angles can affect the landing distance. With no flap, the aircraft will have a much faster approach speed and have very little aerodynamic drag. Therefore, the landing distance will be large. However, with some flap selected, the approach speed is less. There will be more aerodynamic drag and consequently the landing distance will be smaller. However, with full flap, the approach speed is minimal and the aerodynamic drag is maximised. Therefore, the landing distance will be least compared to other flap settings. Having full flap selected for landing allows the aeroplane to maximise its landing mass. However, there is a disadvantage with having full flap if there was a situation where the aeroplane needed to abort the landing and go around for another attempt. You will recall that large flap angles greatly deteriorate the climb performance compared to no flaps. Therefore, in a go-around, after the climb has been established, retract the flaps as soon as possible in the manner prescribed in the aeroplane flight manual. This completes the lesson on general landing performance. In this lesson, you should have learnt and understood all the components affecting the landing, and more importantly, what determines the landing performance. Learn the capabilities of your aeroplane and never attempt to exceed them. Never fall prey to time pressures and never cut corners in your landing preparations or your landing checks. Always prepare for the worst.
This section on Class B single-engine performance will deal with the JAA regulations for all phases of flight for that class of aeroplane. The regulations are all found in JAR Ops 1, which we discussed briefly in the lesson on performance standards. However, most of these regulations can also be found within the CAP 698, which is issued to candidates in the ATPL theoretical examinations, and should normally be issued to student pilots by their ground training organization. If you do not have a copy of the CAP 698, the document may be downloaded from the CAA website. In this first lesson, we will discuss the regulations which are associated with the takeoff phase of flight. However, first of all, there are some general considerations we need to discuss about the operation of Class B single-engine aeroplanes for commercial air transport purposes. These considerations can be found in CAP 698 at the beginning of Section 2 on page 1. There are 4 general requirements about operating Class B single-engine aeroplanes for commercial air transport purposes. The first is that this aeroplane shall not be operated at night. The second, that the aeroplane must not be operated in instrument meteorological conditions, except under special visual flight rules. The third is that this aeroplane must not be operated unless suitable services are available en route, which permit a safe forced landing to be made should the engine failure occur at any point on the route. And lastly, that this type of aeroplane must not be operated above a cloud layer that extends below the relevant minimum safe altitude. The reason why this latter regulation exists is quite easy to understand. If the engine were to fail during these conditions, it would be almost impossible for a pilot to be able to see the landing surface, and therefore impossible for the pilot to carry out a safe forced landing. Further down on page 1 of Section 2, there are some more regulations, but these are specific to the takeoff phase of flight. There is only one principal regulation that must be complied with, and this regulation relates to the minimum field lengths that must be available for takeoff. The takeoff requirements state that if no clearway or stopway is available at the airfield, the takeoff distance multiplied by 1.25 must not exceed the length of takeoff run available. This is best understood by looking at an example. Let us assume that the aeroplane flight manual gives the takeoff distance as 3,000 feet. Multiplying this value by 1.25 gives us a value of 3,750 feet. Essentially, this means that the runway must be at least 3,750 feet long, or, more correctly, the takeoff run available must be at least 3,750 feet long. This rule ensures that once the aeroplane has completed the takeoff, that is, when it's at the screen height, there should be a certain amount of the runway remaining. Therefore, the regulation requirement provides a safety margin for the takeoff. We discussed these safety concerns during the lesson on performance standards. To interpret the regulation, although the actual takeoff distance is 3,000 feet, the authorities are suggesting that the worst case in a million would be a takeoff that is 3,750 feet long. This helps us again to see the difference between net and gross performance. Here the gross performance for takeoff is 3,000 feet, but the net performance, which is always worst performance, is 3,750 feet. If there are stopways and/or clearways, then the regulation requirements are a little more complicated. At airfields with stopways and/or clearways, there are three regulatory concerns about the takeoff distance. Firstly, when a stopway and/or clearway is available, takeoff distance must not exceed the takeoff run available. Secondly, the takeoff distance, when multiplied by 1.3, must not exceed the accelerate stop distance available. Thirdly, the takeoff distance, when multiplied by 1.15, must not exceed the takeoff distance available. Since these regulations may be a little complicated to understand, let's work through an example to illustrate their meaning. We will assume a takeoff distance of 3,000 feet. The first regulation tells us that the takeoff distance of 3,000 feet must not exceed the takeoff run available. Therefore, the pilot must ensure that the runway, or more correctly the takeoff run available, is at least 3,000 feet long. The second regulation tells us that when the takeoff distance is multiplied by 1.3, that distance must not exceed the accelerate stop distance available. If you remember, the accelerate stop distance available is the takeoff run available plus any stopway. So, a pilot must ensure that the airfield has an accelerate stop distance available more than 3,900 feet long. The last regulation tells us that the takeoff distance, when multiplied by 1.15, must not be greater than the takeoff distance available. You may recall that the takeoff distance available is the takeoff run available plus any clearway. Therefore, the pilot must ensure that he has at least 3,450 feet of takeoff distance available. If any of these regulations cannot be complied with, a pilot must reduce his takeoff distance. The most practical method of doing so is to take off with less weight, or perhaps use a higher flap setting, or wait till the air density has increased. Having discussed the regulations detailing the maximum takeoff distance that may be permitted at an airfield, this next part of the lesson will detail the regulations governing how the takeoff distance is actually calculated. These regulations stipulate what correction factors must be applied to the takeoff distance when the runway conditions are different from standard. At the top of page 2 of section 2, under point C in Cap 698, it states that if the runway is other than dry and paved, the following correction factors must be used when determining the takeoff distance. These correction factors are shown on screen. As you have learnt already, grass runways will increase the takeoff distance compared to paved runways. Here, the factor to use to account for the effect of dry grass is 1.2, and 1.3 if the grass is wet. Underneath the table, point D details the corrections to be applied if there is a slope to the runway. It states that a pilot must increase the takeoff distance by 5%, or by a factor of 1.05, for every 1% upslope. However, it also states that no factorization is permitted for downslope. In other words, when an aeroplane may be taking off on a downward sloping runway, no correction factor is to be applied for the downslope. The reason for ignoring the downslope is because a downslope will decrease the takeoff distance, and this helps to add a little extra safety to the takeoff distance calculation. This part of the lesson will deal with how the aeroplane's takeoff distance is actually calculated. All aeroplanes will have either a pilot operating handbook or an aeroplane flight manual. The purpose of these manuals is to show not only how to operate the airplane, but also to detail the airplane's performance.
Shown on screen is an example of the takeoff performance information. This may be either in graphical or tabular format as shown. For the ATPL performance examination, most of the performance data is in graphical form, and therefore the majority of the lessons will present performance data in a graphical format. The example graph we will use is figure 2.1 on page 3 of section 2 in CAP 698. Firstly, the title of the graph indicates that the graph is for calculating the takeoff with no flaps selected. For other flap settings, you may have to consult another graph. Next, take a look at the associated conditions, paying particular notice to the power and flap settings as shown here. Also notice that this graph assumes a runway that is paved, level, and dry. If the runway conditions required for a given calculation are different, then corrections will need to be made to the values this graph will give. We briefly saw these correction factors earlier. Notice this box here, which highlights the rotation and screen speeds for different weights. A pilot must adhere to these accurately because they are the speeds which have been used to construct this graph. If a pilot were to deviate from these speeds, the required aircraft performance would not be achieved. Having looked at the various bits of information around the graph, let's now examine the graph itself. The left-hand carpet of the graph involves the variations of temperature and pressure altitude. This part of the graph accounts for the effect of air density on the takeoff distance. In the example, we will assume a temperature of 15 degrees at an airfield which is situated at a pressure altitude of 4,000 feet. To use the graph then, move upwards from 15 degrees until you have reached the 4,000 foot pressure altitude line. Then move right until you meet the reference line, shown here. The next variable is mass. In our example, let's assume a mass of 3,400 pounds. From the reference line, we must move down along the sloping guidelines until we reach 3,400 pounds as shown here. From this point, we go horizontally to the right until the next reference line. The next variable is wind. In our example, we will assume a 10-knot headwind. Notice, though, that the slopes of the headwind and tailwind lines are different. We therefore recognize that the 150% tailwind and 50% headwind rules that you learnt about in the General Principles for Takeoff lesson have already been applied. Travel down the headwind line until you reach 10 knots headwind, and then move horizontally right once more, up to the last reference line. Remember that the takeoff is not complete until the aeroplane has reached the 50-foot screen height. So from this point on the graph, we must move up the guidelines to the end. Notice that some of the guidelines, such as these, have a divergent or convergent nature. Ensure the line you draw reflects this, so try not to parallel your line to the nearest guideline in such a case. The takeoff distance in our example is approximately 2,300 feet from brake release to the 50-foot screen. However, let us now assume that the runway has a grass surface and that the grass is wet. Remember that both these variables cause an increase in the takeoff distance. Since the graph assumes a paved, dry runway, we will have to make corrections to the takeoff distance for these different conditions. You may recall that wet grass increases the takeoff distance by 30% or by a factor of 1.3. Our calculated takeoff distance was 2,300 feet, but correcting it for wet grass would now make the takeoff distance 2,990 feet. Let us now assume that the runway has an upslope of 1%. Again, you may recall that this would increase the takeoff distance by 5%, or by a factor of 1.05. This now makes the total gross takeoff distance 3,140 feet. To comply with the regulations, you may recall that the takeoff distance must be compared to the available distances at the airfield to ensure it does not exceed the limits laid down by the authorities. To remind you of these regulations, turn to page 1, section 2 in CAP 698. The remaining pages in the takeoff section of CAP 698 are the graphs themselves and various examples on how to calculate the takeoff distance or maximum permissible mass for takeoff. On page 2, section 2, is an example you may follow to calculate the takeoff distance. Page 3 of section 2 is the takeoff distance graph without flap, which we have already used and worked through. Page 4 of section 2 works through an example where, given various field lengths, you can determine the maximum permissible mass you're allowed to carry and still meet the regulatory requirements. Lastly, on page 5 is another takeoff distance graph, but this time assuming that flaps have been selected to the approach setting. Use this graph in an identical way to the one we have already been through. You will need to practice using all the graphs, so ensure you work through the examples in CAP 698 and those in the questions for each lesson. Doing this will help you improve your accuracy in the use of the graphs and help to consolidate your knowledge of the principles you have learned so far. The last part of the lesson will focus on some of the certification specifications for single-engine Class B aeroplanes. These can be found in the document from EASA called CS23. There are only two main specifications that apply to the takeoff phase of flight, and these specifications concern the takeoff speeds. The first of these certification specifications concerns VR. You may recall that VR is the speed at which the pilot makes a control input with the intention of getting the aeroplane out of contact with the runway. The certification specifications state that for the single-engine aeroplane, the speed VR must not be less than VS1. VS1 being the stall speed or the minimum steady flight speed of the aeroplane obtained in a specified configuration. The configuration concerned here is that configuration used for takeoff. The second of the certification specifications concerns the speed of the aeroplane at the screen height. The specifications state that the speed at 15 meters, or 50 feet above the takeoff surface, must be more than the higher of a speed that is safe under all reasonably expected conditions, or 1.2 VS1. You will recall from an earlier lesson that the speed that must be obtained at the screen height is commonly referred to as the takeoff safety speed. The certification regulations about VR and the takeoff safety speed are not found in CAP 698 and therefore must be committed to memory. This completes the lesson on takeoff for the Class B single-engine aeroplane. Familiarize yourself with the format for the aircraft you are flying and correctly adjust the calculated takeoff distance for any variable that is not accounted for in the data. An understanding of the effects of various conditions and factors that control the takeoff will better equip you to ensure that each and every takeoff is well within the limits of the runway available, and thus minimize any chance of an accident occurring. Lastly, do not forget to check the regulation requirements for the takeoff distance.